very good morning, everybody present here, and thank you, students, for coming and joining us in time in a very big number. So today we have come to the third as well as the last day of this workshop. So let me just give a glimpse of what we will be having today. So we will have technical session for 5 and 6 today, and then we'll have a small valediction at the end. So in technical session 5, we will have up to 12 noon, we will have applications of Python, which will be taken by Mr. Parag Bhattacharya. Then from 12 to 12:45, we will have some question answer session, which will be taken up by Mr. Parag Bhattacharya and Dr. Samrat De. And then from 12:45 to 1 o'clock, that's 15 minutes, we'll have valediction. So once more, welcome again to this workshop. And may I now request the speaker, Mr. Parag Bhattacharya, to please take on the session.
Thank you, Amma. Without any delay, let me just begin by sharing my screen. Just let me know if my screen is visible.
Yes. Visible.
Okay, so just to recap, yesterday we had stopped at visualization, that how to do the plotting, different kinds of plotting. So I showed that if you want to do plotting, then we have to use this matplotlib package. Specifically inside the matplotlib package, there is a module called the spyplot, and this spyplot contains all these methods, okay, which can be used to plot many different things, and as well as control the look of the plot. You can make it look even better, even though that part I did not do it yesterday, and I'm going to show it now. So this is how you can import matplotlib.pyplot as PLT. We are using our alias so that it's easier for us to later on we can just access the different functions the way we want to, using by resolving the hierarchy using the dot operator. So first I showed you the basic, how to do a 2D plot. So most basic, the most bare minimum that you require if you want to plot something is you just need a list, that's all. So if I have a list, which I call as Y, which contains these numbers, then I can just say PLT plot Y, and that is going to plot the Y, whatever numbers I have given along the Y axis, and along the X axis, it will be along the horizontal axis, there will be the indices, because I have not provided any data for the X axis. Then I could go and produce one more list which contains the data for the X axis. Then it creates associates, okay, element wise it associates and it creates these set of coordinates, and it just plots these different coordinates in the form of this graph. Then I think yesterday there was a question, okay, the question was how to plot a function, because when I was showing this, so a question had come. I happened to see that question later on. The question was how to plot a function. I think that question has been answered, because the very next thing that I did was I went ahead and I plotted a sine function over 2 cycles. So now it's not that you need only lists for plotting, you can also use a numpy array to plot to use this plt.plot function. So X and Y, one of them could be a list, another one could be an array. Okay, the only thing that matters is both of them, the length should be same. The length of X and the length of Y, both must be the same. So I created a X using linspace. I created points from 0 to 4 pi, 100 points from 0 to 4 pi. And then I created sin X, which was stored as that array was stored in Y. And then simply I plotted X versus Y, and that gives us this nice looking plot here. Then you can also do this. Here what I'm doing is I'm creating the list first. I'm creating the entire thing, both X and Y. I've created initially itself, and then I plotted it. You can do the other way. You can do one more way, that is, you can create a growing list, a list which grows and when you calculate, the list will keep on growing. So that you can do by creating 2 lists, X points and Y points. Then I have these parameters A and B, which is going to define the boundaries of this. So then what I did was, as you move, okay, as AX goes from, in this linspace from A to B in 300 points, then what is going to happen is I'm appending to this list, I'm appending the value of X, and to the Y points list, I'm appending this passing X as a argument inside this function. Now this is a Gaussian function. This is a Gaussian function, and in this Gaussian function there is the center is x naught. Okay, the default values I have kept. So even if you don't give any, even if you don't specify anything, if I don't specify anything, then it is still going to plot, but that is going to be a Gaussian profile which is centered about 1 and having a spread of sorry, centered about 0 and having a spread of 1. So 0 and sigma, I have set it like this, and this is what you get. So you can just control this just by putting some parameters here. You can control the shape of this plot. So here what's happening is the as and it calculates point by point, it calculates, and eventually at the end this it creates a growing list, and finally you just plot the growing list in this way. Then I also showed you how to plot from a file. Okay, so there is this file called spectrum.dat. It's there in that Google shared Google Drive. I have uploaded that. You can download this file and you can just try this out. You can use load.txt, that numpy function which we saw yesterday, which can be used to read data from a file. So you can use that, and then in that we call this spectrum.dat, and I'm giving this argument float to ensure that all the data is saved as float only. And then this data, it creates a, we saw it, the shape of this data. We saw that it was basically number of rows and number of columns were 2. So we want to extract the first column. So how to extract the first column? Keeping all the rows same. All the rows same means we are taking all the rows means we have to use a colon. Colon is going to select all the rows, because if you remember, the first argument inside this brackets, the first index is always rows and the second index is column. So by keeping colon here, that means I'm selecting all the rows, and I'm keeping 0 here, that means I have selected only the first column. So that's why I'm able to extract. This is slicing again. So I have sliced only the first column. Similarly, I have sliced the second column using the second index. I'm putting it as 1 here. So this gives me the two arrays x and y. Okay, and these two arrays, x contains the wavelength in angstroms and y contains the flux. Okay, and then I plot this simply, and I'm getting this absorption line. Okay, with some kind of a broadening effects we're able to see over here. Now next, this is where we had stopped. So next, we would like to customize the plot, because if I just leave the plot like this, it doesn't look nice. So I need to, give some more information. That is, what is along the x-axis, what is along the y-axis. If I could give some kind of labels here, if I could, change the color of the plot, if I could change the thickness of the plot, then that'll be really nice. So we can actually do that. So we can customize this plot and to increase the aesthetics of the plot. But you have to remember that all the aesthetics of the plot, it should come between the plot and the show functions. So here what we did was we had two functions, plot and show. So all the aesthetics, whatever I want to change, it should come between the plot and the show, because show is eventually you're showing it. Okay, you're plotting it. So all the changes, everything that you want to do, you have to do it. All the customization you have to do before calling the show function. Okay, so that's what we need to keep in mind. So first thing, let's talk about modifying the limit, that x limit and y limit. I don't want to show everything. I want to just show a certain range of values. So how do I do that? Consider this. Okay, so here I'm calling matplotlib and numpy because I want to use arrays. So x, I have created an array. I have created an array between from 0 to 6 pi, that is 3 cycles, and 100 points are there. Then y is equal to cos of x. Okay, so now let me just comment these two lines. Okay, so when I run this, you find that it has plotted cos, right? So this is one cycle, this is another cycle, this is one more cycle. So we have got 3 cycles. Now let us say I want to observe the data only between 5 pi and 5 pi. This is from 0 to 6 pi. Okay, this is from 0 to 6 pi, but I want to observe only the this data from pi to 5 pi, not the entire thing. So I can do that by using this plt.xlim. Xlim, it will set the limits of the x values. So plt xlim, okay, starting value is pi and end value is 5 into pi, because I think I have to use np.pi, and here also np.pi. Okay, because I'm taking this pi from this numpy. Okay, so np.pi. So now if I run this, you can find here it is taking, this is pi, okay, and this is 5 pi. It has created. Now let's say here it is showing from the y values. Y value is showing from -1 to +1. So I want to show it, this y limits. I want to make this plot because the plot is going almost to the edge of the figure. Okay, this graph is going almost to the edge of the figure. So I want to have some kind of a padding, some kind of a space between the top, the maximum, and this box, the bounding box. Similarly, I want some kind of space between the minimum and this bounding box. So instead of plotting from +1 to -1 to +1, I could plot between -1.5 and +1.5. So I could do that by using this ylim function, plt.ylim. It sets the limit of the y range of values. So when I do this, you can see here it plots from -1.5 to +1.5. Okay, so you can actually use this to determine which are the places that you'd like to observe. So let's say I want to observe this one. This one contains an absorption line. Okay, so I want to I want to just observe the absorption line. So I can see here, this is 1200, this is 1210, this is 1220. Okay, so let's say I want to observe between 1205 and 1225. Let's say I want to observe from 1205 to 1225. So PLT, I hope this will run. Yes. So we'll do PLT.xlim. I want to observe from 1205, so 1205, all the way till 1225, 1225. You can see here, I'm able to see that specific line. Now I can actually zoom in some more if I want. Let's say I want to go from 1207.5 to 1220, 1207.5 to 1220. I'm able to zoom in even more on this absorption and I'm able to see more features. So these are things that you can actually control. Okay, so that is by modifying the x and y values on the plot using the xlim and ylim. Now let's say I want to add labels. Okay, now the plot does not have any x label and a y label. So I want some label. What is along the x-axis? What is along the y-axis? I want to give that additional information. So you can do that using the x label and the y label functions. This is y label, x label, and the y label functions from matplotlib.pyplot. So let's say again we have a cost. We are plotting the cost function here. So then this one. Let me just comment this to show you the difference. Okay, so this is the plot that we got. We are plotting from -1.5 to +1.5. Now let's say I want to give some label to this x label. I want to plot, I want to show that the value is x. Okay, if I do that, then you can see x is going to appear over here. Okay, we can change the size. It looks very small. I agree, it looks very small, but we can change that. I'll come to that. Okay, but right now it's just getting our grips into how things work here. So now again, if I do this, then I get the cos of x. Right, so x is along along the horizontal axis we have x, along the vertical axis we have cos of x. So we can specify that by using the x label and the y label commands, y label functions. Then yeah, now let's say I want to change the appearance of this plot. Now it is appearing like as a blue color curve. No, so now let's say I want to change the way this plot appears. Instead of a blue color curve, let's say I want to change it to red. Okay, and let's say I want to have dashed lines instead of solid curve. Let's say I want to use dashes. Okay, to do that. So you can actually do that by simply adding some more arguments to the plot command. Okay, to the plot function, you can just add some more arguments. That is going to do the job for you. So we can add the third argument. We can add it something like this. Okay, we can add something like this. So over here, I say the one more command I passed. Let me do it here itself. Or I think. Yeah, we have here the same function. I did it over here. So let me remove this, then you'll see the difference. Okay, when I run this, you'll find that this is again the same blue line. Now let's say I want it to be red and I want it to be dashed. Then I'll add one more argument. That will be a string argument. The color is red and I want it to be dashed. So I put 2 dashes to show that it must be a dashed line. So you can see that it has become dashed line. Okay. So you could have other styles also. You can have, so if I just put a single dash, it will just plot a single solid line. Then if you put double dashes, then it will plot dashed lines. Then if you put O here, if you put O here, then it will plot circles. Okay, I have just given some values here, some representative values you have given here. If I just put a O here, it will plot circles. Wherever all the data points, it will just plot circles. Then if I put dot here, if I put a dot here, it'll just fill this up with dots. Then if I put S here, RS, first one is the color, okay, RS. Okay, so it'll put squares. So suppose I want green squares. If I want green color squares, right? So these are the color values that are available. These are the color values. Other color values also you can actually get, that is by using a hex code. Okay, that is by using a hex code, but I will not do that here, but I don't think we'll have time to actually show that right now. Let's work with this. In case you want to know how to use some other colors also, maybe some other from some other palette, you can just get in touch with me. I'll show you how this is. So right now we'll just focus on whatever is there. So we have R for red, G for green, B for blue, C for cyan, M for magenta, Y for yellow, K for black, okay, W for white, I think. So you can just play around with this. So let's say I want a green colored square. So you just make it as GS. So that is going to give us green colored squares wherever you have the data point. Okay, so you can change the style of the plotting using this. Okay, so now let's say I want to plot multiple functions on the same graph. Okay, I want to plot multiple functions on the same graph. I could do that. Okay, so let's say I have a sine and a cos. Okay, I define X, I define from 0 to 6 pi, 3 cycles. Okay, 200 points. Then Y1 is the first function. Y1 is going to take sine values, and Y2 is going to take cos values. Then I'm going to take two plots. So let me do it just one by one. Okay, let me just do this. This is a basic, sine plot. I had put B double dash, that means blue, dashed blue line. It will plot a dashed blue line. This is for sine. Okay, dashed blue line. This is for sine. Now I want to, let's say, plot one more. Then what you have to do is you have to give one more plot command. Plot Y2, that is Y2 contains the cos functions. So you'll plot Y2 now with respect to same X. X will be same, but Y will change. For in this case Y1 because it's sine. In this case Y2 because it's cos, but this time I want a solid red line. Okay, I want a solid red line, so I'll just put a R dash and run this. So you can see a solid red line that represents your cos function. Okay, so now of course you can put the limits here. I want to plot between minus 1.2 to plus 1.2, X label and Y label. So that is going to give us a more meaningful graph like this. So like that you can have as many graphs as you can, as many as you want. Okay, as many as you want. So you could have something like let's say y3 is equal to np, let's say x times np dot sine x. Okay, let's say this is what this. I could just add one more plot here, plt dot plot. So x comma y3, x comma y3, and let's say this one I would like to plot in green, dots. Okay. Okay, so we got these green dots over here. It's not looking nice, so let me just use a solid line. Okay, so this is actually going off because I have I have not taken the range here. So let me just make this scale it down a little bit. That's 0.1 times this. Yeah, so you see this green plot, this is, you're plotting x into sine x, into sine x. So the same sine x, it is going to just go on increasing. Okay, maybe I could just change the limits here, x limits, y limits. Let me make it as 2 and 2, minus 2 and plus 2. So you're able to see the third plot over here. So you can control the way your plots look like. You can just add as many plots as you want. Okay, so this is how you can have multiple plots on the multiple functions on the same graph. You can also have another from a file also. You could take from a file. Let's say you have some data which is stored in the file, and you can just plot all the data. And then let's say you're trying to have a model, let's say a theoretical model which is trying to explain the data in the file. So that theoretical model also you can plot right on top just to see whether the experimental data in the file, if it is matching your theoretical model. So all of this you can do that. Just you can have a multiple plot like this. So that is going to give you a lot of insight. Then let's say I want to plot this one. I want to plot a Gaussian function. Okay, y equal to e to the power minus x square. Now we'll now slowly we'll do some more things. We'll try. Now I'd like to make these labels even better. I would like to increase the length, size of the label, and so on. So let's do that. So what I'm going to do is I'll do it more gracefully this time. I will just create a function y of x. What this function is going to do is it's just going to return this. It's just going to return this. It's going to return e to the power minus x square. So whatever x you send, it's going to return e to the power minus x square. So this is the what y of x function is going to do. So let us go ahead and we'll define some limits. A is -5, B is +5. And then we'll define your x values. We'll define on a linspace. Okay, so A, B, okay, we could take 100 because that will make it more smooth. So A, B till 100. Now you can plot this. Let me just comment all of these to show you the difference. Okay. First, I'll do the basic plot. The basic plot is simply x comma y of x. Basic plot is simply x comma y of x. Run this, and we got this Gaussian plot that we wanted. Okay. So now let's say I want to change the color. I want to make it black. So I'm just going to add one more argument to it. C equals K. K stands for black color. So it has plotted a black color. Okay. So now you can have, you can do something like this. Let's say I want black dotted line. Okay. I can do something like this. Okay. I can do black dotted line, but you can also do it this way. This dotted line, same thing. C equals K, that controls the color. If you want further control, more fine control, and the line style, okay, that dashed line that you wanted, you could split this up like this. Okay, so that way also this will work. Okay, so LS means a line style. Okay, so we'll just keep it as dash. I think there is dot dash also you can do. No, it doesn't work. Or O dash. No. Let's keep it a solid line. Okay. Now I want to change the line width. That is the thickness of this line. Okay. I want to change it. Let's say I want to make it as line width equals, let's say 2. Okay. Line width is 2. So you can see here it has become slightly thicker. It may not be so visible because very small change can actually, okay, you can see the line has now become thicker. Okay, now let's say I want to put some markers also. Okay, apart from these lines, apart from this curve, wherever the data points are, I want to put some marker also. Okay, I want to put dots. Okay, I want to put dots as the marker. Okay, so I say that marker is dots. Run this. So it has put dots over here, but these dots they're not visible. Okay, these dots, they're not visible. I can make this visible. First of all, let me change the color. Okay, so MFC means marker face color. MFC means marker face color. Okay, I'm putting it as red. MFC marker face color. I'm making it as red. So you can see this will be red. It's not so clear now because the size is very small. Okay, the edge color also, MEC means marker edge color. That also I'll keep it as red. Okay, now it's looking slightly better. It's looking like, okay, there are some red dots here. Then let me increase the marker size a little bit. Okay, marker size, the parameter is MS. Let's make it as, let's say 5. Marker size is 5, not much difference. So let's say I make it as 10. Now you see the marker size has become bigger. Okay, now you see here, the markers, there are lots of markers here. Okay, lots of markers here. We don't want to mark all of them, so just say mark every, you make it as none. I'll show you how to control this. Mark every, you make it as none. It won't mark all this, so we'll control this a little bit later. using this mark every, I can control this. I think I can show you now, right now itself. Okay, by the way, some of you might be wondering as to how the hell do we remember all of these parameters, right? You don't have to remember. The way I'm able to remember is because I have already commented this line here, and I'm just looking at this line and I'm writing this. Okay, so already this line is available with me, but does it mean that you have to copy and paste this line? Not required. You just have to go to this URL. Just go here. It will give you all these parameters that we have. Okay, so for the plot command, what are the parameters is given right here. Okay, so when you go to this one, okay, so here you can see all these parameters that I have used. It's somewhere over here, that MEC, MFC, marker, MFC, MEC, all of these, you'll find it over here. Marker, okay, it will be a string. Okay, what will be the style of the string? Then marker edge color, MEC, okay, it's a color. Then MFC, okay, MFC, that's a color. You can also control the marker edge width. That will become clear if I just increase the marker size a little bit. It'll become even better. So let's make it at 15, and marker edge color, let's say instead of red, let me make it as blue. Okay, you can see, so we are having markers which are inside there is red and outside there is blue. And then you can change the thickness of the edge also. Okay, you can change the thickness, marker edge width. You can change this using MEW, this parameter. Then marker size MS, that's the marker size. It's given very clearly over here. Then a mark every, what are the values? You could have some int values, none or int. So let me just try this out, what happens. So here I have given none. Let me make it as int. Let's say I give 2. Okay, you can see the density of these dots have decreased. Okay, so what it has done is it has only put every alternate point, it has put a marker. That's what it has done. So I could reduce the density even more if I put 3. So every third point, it is going to put a marker here. You can make it you can reduce it even further. You could make it 5. So every 5 points, it is going to put a marker here. So like that, you can control the density of these markers on this plot. Then yeah, so we can put a label here. So here also, this is also given over here. You can, it's given. The best thing is all these parameters, these properties, they're given in alphabetical order. So you could just go here and then you can just look whatever you're trying to find. You can just go here. So I'm looking for the label here. So label is given here. You can use a label here. So label. Okay, so now let me just show you something. Okay, so let us say label equals f of x equals e to the power x square. Okay, e to the power x square, e to the power minus x square. So I do something like this. Okay, let's run this. I think I have to do this. Yes. Okay, the moment I put a label, I want to show, okay, this is the plot. What is the label of this plot? The label of the plot, I have, written it as f of x equals e to the power minus x square. F of x equals e to the power minus x square. And then this label will not appear until and unless you say plt.legend. Okay, plt.legend, because the label will be put as a legend like this. Okay, so if this command is not there, then you will not get whatever label you put. It will not be displayed. It will be displayed only if you enable the legend here. So now you can see here, legend, there is a parameter called as LOC. That means location. What is the location of the legend that you want, wherever you want to place it? So there are many options. I think it's over here, legend. It should be somewhere here. No, I can find out and I can give you the link where these options are. So I use best. Okay, it's a string called best. Then Python is going to decide, matplotlib is going to decide which is the best location for the legend to be put. So it's going to generally put, when you say best, it's going to put in a place where there is no data points. So it's going to put it in a place where wherever there is least number of data points, over there it is going to place the legend here. Now let me run this here and see the legend. But this is not something that looks nice. You see, what is the function? The function is e to the power minus x square. I want e superscript x, sorry, e superscript minus x, and to that x there is another superscript x square, but it is not looking anything like that. It is e, then a hat, then inside curly brackets minus x hat 2. So this looks like LaTeX command, right? If those of you have attended those of you have attended a LaTeX workshop, you know that this looks like a LaTeX command. You can use this kind of commands in LaTeX. So what we can do is I can actually render this using LaTeX. Okay, and the way to do that is just put a $sign before and a $sign afterwards. Put a $sign before and after. Now when you run this, you can see here this is coming correctly. So e to the power minus x square. Okay, so it is showing me the way I want it without those brackets. So it's going to basically use LaTeX to understand what this is, and it is going to render the text in this way. Okay. So that was the plot one. So now we can put label. Now the same thing, the LaTeX rendering, you can do it in the X and Y also. So over here, okay, over here, I can use LaTeX rendering here also. X, and here in LaTeX we use sign of X. Sign is a function, sign is a command by itself. Sign of X, and similarly here. Cos of x. Okay, so it is going to create sine x and cos x. Okay, so now same thing you can apply it for the label also. So label this. So it's going to put x and f of x here. Then I want to put a title to this plot. Okay, some title. This is a Gaussian function. So plt.title, that is going to set the title to this. It's going to give on top. It's going to call this Gaussian function. Then of course you can have your x limits and y limits. X limits between minus 5 and plus 5. Okay, minus and 5 and plus 5, minus 5 and plus 5, and y limit because the maximum value is 1. Maximum value is 1. So one way by which I can do that is, it's always good to have around 10% space above your maximum. Okay, wherever the maximum is, between the maximum and the top of the plot, it's always good to have around 10% space. So you can do that in this way. The minimum is 0, and even same thing, wherever it is minimum, the edge should be around 10% below. So you should have some 10% space above, 10% space below. So you can do it this way. So here it is 0, so I don't have to worry about the minimum. It's looking fine. So 10% of this is 1.1 times whatever is the maximum, of. Okay, for that I just create the array first. That will make it faster. So y, let's say I call this function as f. So y equals f of x, and here I'll just put y. Okay, so I can now find out the maximum value of y. So wherever it is, it's going to use that, and it's going to give that as the limit of the y. You can see here we are having some 10% space. So similarly, minimum 0, maybe minus 0.1. Okay, so that is going to give us some nice space above and below. And finally, let's say I want to show some grid. Okay, you want to put some grid and on which the graph is plotted. So when you do that, it is going to show the grid. So over there you can actually now correlate which points, where do the different points they lie. Okay, so we can plot this easily like this. So this is some aesthetics. Okay, so you can follow this page. Okay, and you can get the more details about all these parameters that I have used over here. Okay, any questions so far? Any questions? Does anybody have any questions before I move on to the next topic?
Yes, sir.
Yeah, one more.
Sir, actually, yes, sir. In a function, in a plot function, how many arguments? What's the limit of adding arguments?
Okay. Yesterday I was talking about the kind of arguments, no? There's positional arguments, keyword arguments, default arguments, and so on. So there was one more possibility. Under positional and keyword arguments, you could have variable positional and variable keyword arguments. Okay, so how many are possible? You have to go to this page, and you have to see all of these are possible. Okay, all of these arguments are possible. So you can basically count this 1, 2, 3, 4, just count these. So you can have all of these as your arguments, or you can have none of these also as arguments. It's totally up to you. Okay, so upper limit will be whatever are the properties that is available on this table. Is that okay? Don't worry. Does that answer your question?
Yes, sir. And sir, can we add animation in Python?
Yes, we can. We can do animation, but I'm not going to do that. If you're interested, I can show it to you. In fact, these resources for animation is there in the Matplotlib. I can show you. You can go to examples, and there are lots of animations. Usually, this is the easier way out. Okay, so whenever I'm like, I don't have time to actually, learn how to do this. So generally, this is what I do. I just go to the examples, and somewhere there should be some animations. Let's see. I think I saw yesterday some animated plots. Yeah, you can have some animations. You can have plots like this. You just have to go to this. So whichever you're looking for, let's say you want to do this, right? Just open this, and that is going to give you the code. The code will be available. Okay, so you have to, of course, you have to import all these packages also. So you can just take the code from here, just copy. I mean, you just have to click here. It will copy the code and paste it, and then see how it works. Then you just have to play around with your variables and see where it is. Okay, so you can try this out for yourself. Okay, so that's how the animation is going to play out. So you can play only once. You can play as a loop. You could have a reflect. I think reflect means it will go back and forth. Okay, something like this. I mean, you all will be knowing about this. In Instagram, you have some features like this. No, I think it's boomerang or something like that. So these kind of things you can have. Okay,
Yes,
don't worry.
sir.
Okay, so I don't know. I don't know much. I don't use
Yes, sir.
much, so I won't know much about it. So you can try this out. Okay, so you can do animations like this. So answer is yes. Okay, you can do animations like this. Okay, any other questions? Okay, so let me just proceed then. So next thing that we want to do. So now that we have customized the plot the way we want it, we want to, let's say, save the plot. Okay, we want to save it as a figure because you may want to, include this image inside your document. Let's say you're writing a thesis. In your thesis, you'd like to put this image. So generally, what do? We just take a screenshot, but screenshot is not a good. It's not a very good way of doing things, because screenshot you will be capturing only at a resolution of the screen, no, only whatever is the resolution of the screen. We want to have control over the resolution so that when you zoom in, okay, the image does not look bad. Okay, when you zoom in, it does not look pixelized. It should have a very nice clean vectorized image. So for that, you can actually save plots also in Matplotlib. I can show you. We'll do I'll add a couple of plots over here. So let's say we have two functions here. The first function is e to the power minus x cos twice pi x. Okay, let me just write down the functions here. So we have y1 of x. I hope it is rendering. Oh, yeah. Y1 of x is equal to e to the power minus x, and we have cos 2 pi x. Okay, so this is the first function, and the second function is simply y2 of x is equal to simply cos pi x by 4. Simply cos This is, by the way, what I'm doing is LaTeX coding. Okay, I'm just coding this in LaTeX. So that means in Python workshop, you're getting LaTeX knowledge also. Pi x divided by 4. Oops. Right, RIGHT. Okay, so these are the two functions that we want to plot over here. Okay, so I defined the first function def, first function y1 is this, and I defined the second function def y2 is equal to this. So whatever x value you put, it is just going to calculate according to these two functions. So we choose x, a and b. Okay, lower and the upper limit. We want to make the plot between 0 and 10. We want to make the plot here. Then I define your x values, 1000 points, starting at A and ending at B, 1000 points. Then I plot the first one. Let's just plot it first. Okay, so this is the first plot. Okay, this is your y1 of x. Okay, this is y1 of x. So I have plotted in red color. The line width was 3, which is a little bit too much for me. So let me reduce this, make it as 2.5. Okay, now it's better. So there is a label here, but I put some label here, but the label is not going to appear right now because I have not put on the legend here, but we'll do this a little bit later. Next. Okay. So this is going to plot the next one. Okay, so which is basically a cosine plot. Okay, so it's going to plot this here. Then we put the x label and the y label, x label and the y label. Okay, so now you can control the size of the x label. Let me just remove this and show it to you. Okay, so x label, the x looks very small. The x looks very small. So I can just put one more, argument here under the label. Okay, for the x label, I can just put one more argument here. The argument is size equals 12. So if you want to know what are the arguments, what are the parameters, you can just Google search for matplotlib pyplot x label, whichever you're trying to find out. Just go to this one, the documentation, matplotlib documentation, x label. So I think you should get here, not here. Size, I think it should be here, 3.3.3. Should be somewhere here. Okay, I'll find this out and I'll provide the links here, but you can do that. Okay. All right, coming back to this. So size is, let's say I make it as 12. Okay, size I make it as 12. You can see the x has become bigger now. You can increase this some more. If you're not satisfied with this, you could make it 16. Okay, so you see now x is much clearer. In a similar way, you could do that for the y label also. Make it 16. Okay, so we have f of x. Now we put the title here. The title is, f of x, or I just put an ordinate title here. y1 of x, y1 of x, and y2 of x. Size is 12. I'll increase this size also. I'll make it, let's say 18, slightly bigger. Okay. Okay, so this is the way by which you can control the size of the font. Okay, you can make it look even more clearer. Then we put some limits here. Xlim is this, ylim is this. Now this is one more thing, is you want to put some ticks, right, on the x-axis. So you can put x ticks. Okay, you can see here, you can see smaller ticks here. Just see the difference. So it has plot 0. After 0, it has put 2. Then it has put 4, 6, 8, and so on. Okay. You can just, if I put x plt.x ticks, then what I'm going to do is I create a array from A to B. From A to B, A is 0 and B is 10. okay, in steps of 1, b plus 1. So because I'm including 10 also, so because a range does not include the endpoint, so I have to just make it slightly more than the endpoint. So b, I'll just make it as b plus 1, so it's 11. So that means from 0 to 10, and then in steps of 1, in one steps of 1, it is going to do the x text, and then size of the text is 14, and no rotation is 0. It should be vertical because these are x text, and you can see it has plotted here. But let's say if I make it in steps of 0.5, if I make it 0.5, you can see some more text will come over here. You can see here, you can see some more points, but this is not looking good. Okay, this is not looking good. So you just put whatever is looking, making our plot look more attractive. So 1, 2, 3, 4. Now this is looking better. Okay, so now you can add a grid also. Okay, you can add a grid also. Then you can put some text here, plot of multiple functions if you want. Size of the text you can change. Now if I put legend, location is best, okay, then it is going to just find out what is the best location. So whatever is the label that I have mentioned over here and here, that legend will now appear on the graph. Okay, so now next thing is save fig. Okay, now let's say what will happen is wherever your Python program is running, okay, wherever your program is running, that same place it will store this. So right now this program, okay, WCP 20 day 02 underscore 20, 04, okay, 0204, okay, this is the notebook, okay, day, WCP 20 day 0204, this is the notebook. So it is going to create a file in the same folder wherever the notebook is existing. It will create a file in the very same folder. Okay, so let me just keep this folder always on the screen, and you can see here when I run this plt.savefig, when I run this, you can see that it is going to create one more file that will be a PNG file. So always save your figures as PNG files. PNG stands for Portable Network Graphics. It basically creates very clean vector images. Don't try not to save as JPEG. Okay, JPEG actually reduces your it does compression. So as a result, it reduces, it compromises on your quality also. So always save your figures. If it's a figure, always save it as a PNG file. Okay, so fname, the file name is equal to multiplot.png, and when I run this, you can see one more file has got created here, multiplot.png, in the very same folder. Okay, so if I open this, this is the file. Okay, but what's the problem with this file? What's the problem? Let's go full screen. You see, the resolution is very less. You see, when I zoom in, when I make it full screen, you can see it has become blurred, kind of, it gets blurred. You see, fx, y1x, y2x, all of these, they have kind of got blurred when you make it full screen. Okay, so how do we avoid that? We want to increase the quality, we want to improve the quality of the plot. Okay, you can actually do that. There is a parameter which can be used to improve the quality of the plot, that is called as DPI. DPI means dots per inch. Okay, how many dots per inch in the figure? In 1 inch, how many dots are you going to use? More the dots per inch, better is going to be the plot. Okay, so there is this parameter called as DPI. I'll show you for a small one. Let's say I take 50 dots per inch. Okay, I'll show the difference. It has created this. Now this is the file. Open this. You see, it's actually got worse because there are less number of dots in per unit area. There are less number of dots. So as a result, it has got worse. Okay, now let me just increase this dots per inch. If I make it as, instead of 50, let's make it as 100. Okay, now let's open this. Definitely better, right? The resolution. Now the text has become even clearer. Generally, personally, I find for figures, 200 DPI is a good, good way, good for printing. If you want to print this out, 200 DPI is good enough. The file size is not so large also, and at the same time, it looks really nice also. So you can see here, this looks much better. The images, the text is much sharper. You can go for 300 also. That is also fine. 300 DPI. The more the resolution, the better it is, but the compromise is the size of the file will increase. Okay, it is 117. Okay, right now you can see here it's 117.6 kilobytes. That's the size of the file. You can see it's become even better now. So now this looks like a plot which you can actually print out, and you can put it on your thesis. It will look really nice. Okay, You can see the size has also got bigger. So that's how you can control the this quality of the image that you are producing. So how do I get this? You can just go to this link. Go to this link. This is for SaveFig. For SaveFig, you go to this link, and here you will see this is what I was talking DPI. Okay, dots per inch. The resolution in dots per inch. Then if you want to save what kind of quality, I mean, generally don't change this, because like I said, don't use JPEG. Then lots of other parameters are also there, which you can just play around, and you can see what difference does it make to the plot. You can also plot it as a PDF. Okay, you can also plot it as a, you can also save it as a PDF. I think I'll show you how to do that. PDF, and I think here I have to say format equals PDF. Format is a string. Yes. One more parameter I can give. Format equals PDF. It has created a PDF file. Okay, open this. Okay, so this is in the same, with the same resolution, it creates a PDF file. Okay, so that's how you can save your plot. So let me just change it back to PNG. And if you do PNG, then you don't have to do this. By default it's PNG. Okay, so that's how you can save your files. Okay, you add different qualities. Okay, then next is, yeah, one more thing. Next is adding subplots. Sometimes, okay, we want to add subplots to it. You can see, you have seen some figures where multiple plots are there. Okay, so this code I have just taken from the code which was provided to me in that workshop which I had attended in Kolkata. So I just picked up the code from there, and I just changed some of these text that appears over here. Okay, so I'd like to give credit to the fact that I have just taken the code just to show you, just to give a demo here. So we have, this is the function that we're using, x to the power 1.3 by 2 into e to the power minus x. This is the function. The function is y of x equals x raised to the power 1.5, that is 3 by 2, and e raised to the power minus x. Okay, so this is the function. So whatever x you put, it just calculates according to this formula, and it will return the value. Okay, so a range, we define some of these we define the x range of x values. Then whenever you want to, suppose you want to add subplots, you want to add more than one plot. So in that case, we don't use the PLT command. We have to first create a figure. So for doing that, let me just tell you what this difference between figure and axis. You can see this fig and AX. Fig and AX, you are able to see that. So for that, you have to know the difference between a figure and an axis. Okay, so let me just show you. Maybe I can just use something like PowerPoint to show you. Okay, so this is what I want. Let's say I want 4 subplots, 4 smaller plots. Okay, so this is one subplot. This is one subplot I want. Then this is another subplot. Okay, so these are the 4 subplots. So we could have some kind of I could have some kind of a curve here. You see some plot like this. Okay, so suppose I'm having some plot like this. Okay. Oops. Okay. So let's say I create just copies of this. Maybe I could just flip this over. Then we have another plot over here. Okay, so let's say these are 4 subplots. Okay, so what you have to understand is the difference between figure and axis. Okay, so the figure means the entire thing, whatever appears on the screen. Okay, so figure is this whole thing, this entire big box. That's a figure. Okay, and the subplot is the individual graphs that you are having. That is known as axis. So difference between figure and axis is figure is the entire thing. Axis is the individual plots that you're having, that is known as an axis. Now we understand axis in a different way, but in Python, this is what it means. The individual plots that we have. This is an axis, this is an axis, then this is an axis, and this is an axis. All 4. There are 4 axes. In this figure, there are 4 axes. So figure is the entire thing, and axes are the individual plots that I'm making here. So this is the difference between figure and axis. Okay, so let's say I want to make 4 plots, 4 subplots. Each subplot will be one axis. Okay, each subplot will be one axis, and all of these subplots will lie in the same figure. Okay, so figure will have, outside will have a figure, and inside this figure we'll have 4 subplots, which are the 4 axes. So this is how it's going to work, the hierarchy. This is what it's going to work. So we'll have something like figure. Okay, so we'll have figure, and inside this figure we'll have axis 1, then we'll have axis 2, then we'll have axis 3, and then we'll have axis 4. Okay, so these are the 4. This axis 1 is the subplot 1, is the first subplot that we're looking for. Axis 1 is nothing but your subplot 1. Similarly, axis 2 is nothing but your subplot 2. Axis 3 is the subplot 3, and axis 4 will be the subplot 4. Okay, there's a nice diagram which is available. I'll find this diagram and I'll share the diagram also with you. So this is what you need to keep in mind. Okay, figure means the entire thing. Axis means the individual graphs that you're putting. Okay, so it's not the same as the way we understand axis in Python. This is how it is done. This is the hierarchy. So you can see here what we are doing is this. Fig. What is fig? Fig is a figure. Fig is a figure. Okay. So fig is a figure, and I'm passing some arguments. The argument says fig size. Fig size, I'm putting it as 10, 10. That means the figure size that we have here, if you want to correlate this with what we have here, when we say fig size is 10, this is what we mean. Fig size is 10. This is what we mean. 10, 10. The width of the figure is 10. The width of this figure 10. Okay, and the height of the figure is also 10. Just a second. The height of this figure is also 10 inches. Okay, that's what it means. Even though in this figure it doesn't look like that, but the height is also 10. So we are creating a figure. We are creating a figure which is 10 cross 10. Width is 10 and height is 10. Okay? So this is what I mean by putting this as argument. The size of the figure, the canvas that we have created. So figure is like the canvas. Okay, you can think of it that way. Then what we do is we create axis. This is the first axis. Now you know what is an axis. What is the axis? Axis are the individual plots, individual subplots. So figure axis 1, I call it as axis 1. Then what I do is, where am I adding the axis? You can add new axis using this function called as add subplot. You can use add subplot to add a axis. And where are we adding this axis? You can see the parent where I'm adding the axis is fig. That means, what this means is, to this figure, you add one axis. So that's why it's fig dot add. Okay, then next, axis 2 is fig dot again add subplot. That means into the same figure you add one more subplot. Then to the same figure you add one more subplot, which I call as AX3 and AX4. So this is what happens. So AX1, AX2, AX3, AX4. So when I call this, okay, so this is your fig. When I call this command fig, it will create the figure. Okay, this is a figure, and fig dot add subplot ax1, fig dot add subplot ax1 equal to fig dot add subplot. Okay, it's going to create ax1. Next, fig dot add subplot ax2 equal to fig dot x add subplot is going to create the second axis as this next subplot. Next, when you do fig ax3 is equal to fig dot add subplot, we are creating one more. Okay, and then lastly you create this. Okay, all right, so now how can we be so sure that these are the axes that is created? It could be some other things also. You can mention it here by the arguments. You see, the first argument is 2 cross 2. The first argument is 2 cross 2. You look at the axis as a matrix. If you look at the axis as a matrix, these are the elements of the matrix. So how many rows and how many columns are we having? We are having 2 rows and we are having 2 columns. 2 rows and 2 columns. Okay, so because we are having 2 rows and 2 columns, so that's why the first 2 arguments will always be 2, 2. Okay, because we are having 2 rows and 2 columns. Next, what is this 1, 2, 3 and 4? 1, 2, 3 and 4 is a number that is given. Generally, the order that is followed is the numbering that is given to the subplots. Generally, the ordering that is followed is left to right, top to bottom. That's how we give the numbering. So this is number 1. This is axis number 1. This is subplot number 1. This is subplot number 1. Okay. This is subplot number 1. This is subplot number 2. Okay, left to right, and like I said, top to bottom. Then you go down again, left to right. This is subplot number 3, and this is subplot number 4. Subplot number 4. So if you want AX1, let me shift this whole thing here. Okay, AX1, then you have to tell AX1, this is the subplot, and this subplot, where does it exist? Let me reduce the size of the font a little bit. Okay. I want to exactly identify AX1. Okay, I want to identify the first axis. So how do we go about doing that? We can mention this axis, the coordinates of the axis, we could mention it using this in this way. So how many rows are there? How many rows are there? There are 2 rows of axis. There are 2 rows of axis. How many columns are there? There are 2 columns of different axes. Then AX1, which is AX1, AX1 is this one. What is the number of this figure? The number of this figure is 1. So this next argument will be 1. Okay. For AX2, the second axis, number of rows, number of columns will be same, but this figure number is, this subplot number is not figure, this subplot, this axis number is 2, so it will be 2. So that's how you can associate. Then next one, it will be 3, because this is what I want, and this numbering is 3. And lastly, we have 4. So using this, you are able to identify which is what, which figure is what. So now all we need to do is just refer to them using AX1, AX2, and so on. So AX1 is, you are doing this. So this part, it creates the figure. This line, it creates the figure. This line, it adds all of these subplots to the figure. All of these different axes, it adds to the figure. Then there is something called a super title. Super title is the title that will appear somewhere over here. Okay. So this is where the super title will appear. This is your subtitle, because we want a title just above the entire figure. The entire figure. What is the figure? What is the figure? Entire figure. What is it all about? Okay. What are you trying to show in this figure? Okay. So this should appear directly above the figure. Let me put this here inside. Okay. So this is your super title. Okay, the super title, it is going to put whatever you text you have here is going to just place this over here. Next comes the plotting part. Okay, next comes the plotting part. So what we'll do is we'll have we have used here 4 different plots are used. One is a normal plot. Another one is a semi-log x plot. Semi-log x plot. The other one is a semi-log y plot, and finally log. So semi-log x means the x-axis will be the spacing will be shown logarithmically. Only the x-axis will be logarithmic, y-axis will be linear. Semi-log y means the y-axis. Okay, the y-axis that is f of x, that will be shown in logarithmic way, but x-axis will still remain linear. Log means both x and y-axis, both of them will be logarithmically spaced. Plot is linear, both x and y are linear. Semi-log x, only x-axis will be logarithmically spaced. Semi-log y, only y-axis will be logarithmically spaced, and log means both x and y will be logarithmically spaced. So if you're having data which is having a very large variation, so you can use all of these plots. Let's say we are having data where x, the horizontal axis, the data is varying linearly, but the vertical axis, the data is varying logarithmically, then you can use semi-log y. Okay, so this is what we want to plot over here. So then what I do is, you just need to add those plots here. So ax1 dot plot, I do this. Okay, so I'll just do it one by one. Let me just comment out these, and then we'll see the difference. Okay, so what I've done is I have created the axis, and then now I want to plot this. So when I run this, okay, you see it has created the plots. It has created 4 plots. It has created 4 different axes, and you can see here the super title. The super title is this, which basically I'm writing this function. It is appearing in the super title. Now I have, it just creates these 4 plots. Okay, it just creates these 4 plots. Okay, it creates these 4 different plots, but I have added only to the first one. I have added only to ax1. ax1, axis 1 is this one. Now let's say I want to add to ax4. Let's see. If I run this, what will happen is this will get filled up, because this is 1, 2, 3, 4. Okay, I'm plotting ax4, and ax4 is 2, 2, 4. 2 rows, 2 columns, and the plot number is 4. So this is what is going to happen here. Let me run this. Okay, you see that it has plotted over here. Okay, so now we can put some text here. Font size, I'm keeping it as 12, and I put some text here. Okay, so this is a normal plot, and this is a log plot. Okay, this is black, and this is in green. Then you can go in and plot the other ones. So this one, if I do ax3, then it is going to plot ax3. ax3 is 2, 2, 3, 2, 2, 3, 1, 2, 3. It is going to plot here. Okay, it is plot as expected. This is plot here, and then finally the last one. Okay, it is plotted here also. Then you can actually choose to save this figure. I use DPI equal to 300, DPI equals 300. That's the plot. Okay, you can zoom in and you can see it's at a very good resolution. For printing, it's really good. Okay, so this is how you can add many different subplots. I can show you one more thing just to show you that this is indeed the case. Let me just put 3 plots. Okay, let me just put 3 plots here. I'll just remove the 4th one. I'll just remove the 4th one. I'll just remove the 4th plot. I'll have only 3 plots, but I want all of these plots to come one below the other. Okay, so I want 3 rows and 1 column. I want 3 rows, because there are 3 plots and all of them should come one below the other. Then you'll see the difference here. Okay, let me remove this 4th plot as well. You can see here, this is what I got. Okay, 3, 1, number of rows of figure, number of rows of axis is 3, number of columns of axis is 3. 3 rows and columns is 1. 3 rows, 1 column. Now I could have all 4 of them one below the other also. That also I can do. So I could just have 4, 1. That will create all 4. Okay, that will create all 4. So the numbering, like I said, it will be from left to right, top to bottom. So here there is no left to right because there is only 1 column. So it will go from top to bottom. 1, 2, 3, and the last one will be 4. Let me remove this. Okay, so this is the plot that we got. Okay, if you want to change this, if you want to swap, right? If you want to swap, this normal plot, if you want to bring it below, and the log plot, let's say you want to bring it on top, you can do that. All you need to do is just change this the normal plot, this AX1, you make it as AX4 and AX1. Okay, and when I do that, normal plot will go below. Okay, normal has gone below and the log has come up. You can just do the swapping here itself. Much easier to work with. Okay, any questions? Any questions regarding subplots? The best way to learn is actually, of course, to play around with this. Just go online and just open a notebook and just play around with this. That is going to give you a lot of insights. In fact, you learn more when you do mistakes actually. Read the error messages. Error messages are very important. All right, so now next we'll go to plotting histograms, because this is something that, if you're doing statistical data, you might be interested in histograms. Okay, so you can plot histograms using this matplotlib as well. So let us say I just create a distribution, a random distribution, okay? Because you saw yesterday np.random, right? np.random, and we used uniform. So let's just see the uniform first. I'll just show using uniform, okay? So what it does is it creates a uniform distribution from 0 to 0.1. It creates a uniform distribution, and in this it just takes 5,000 samples, okay? And all of these it creates an array, okay? 5,000 random numbers in this interval 0 to 0.01. Between 0 and 0.01, it creates 500 random numbers. Okay, and this is a uniform distribution. So every random number, every number from 0 to 0.01 has got an equal probability of being chosen. Okay, and this array it saves in n. So this n is an array of, it's a single row, 1 row, and 5,000 columns. Okay, so then I want to find out what is the distribution. You can write your own function to that, but matplotlib, it provides you with a hist function. The hist function does that for you. Okay, so hist function, what I do is plt.hist, I put whatever is the array that contains my data, I put as the first argument, and then I put the bin size. I'll show you when we get the histogram, we will see the bin size. This is not a normal, this is a uniform distribution. Okay, size is 12, title, I keep this 12, let me run this. You see, as expected, because it's a uniform distribution, all the numbers have got almost the same probability of being generated. Okay, instead of 5,000, let's make it as 10,000, then it will become even more uniform. can see they're more or less uniform. Okay, so let's change this now. Instead of uniform, let's make it normal. Okay, normal, what should happen? You should have a Gaussian distribution. You should have a Gaussian distribution. Run this, you see the Gaussian distribution like this. Okay, so now some more controls on the histograms. There is a link which I have given here. Some more controls. Let me go here to this link. Okay, so this is the these will give you the parameters for the hist function. So plt.hist n50. Okay, so now next argument is 50. Let's change it. This is number of bins. Okay, here 50. So this is the number of bins. Histogram, we have bin sizes. So number of bins is equal to 50. Now let's say I make it 10. Number of bins, I want to make it as 10. 10, you see the difference? You see, you can immediately make out what is the difference. Okay, 10 means you take 10 such bins, and what are the numbers? All the numbers that lie within this bin, that is, you're taken as one single set of one count. Okay, for that particular bin, you can have increase it to 100. Okay, number of bins, increase it to 100. You'll see much more granularity. Okay, so number of bins in this case is 100. Now, but then this is not looking nice because I'm not able to distinguish between the individual bins. So let me just go back to 50. I'll go back to 50 bins. I'm not able to distinguish between the individual bins because it will be nice if you can see some kind of lines which will segregate the different bins. You can do that. You go to this matplotlib, you can see the parameters which are available, bins. Okay, you could also use your keyword argument. You could just say bins equals 50. That will also work. Okay, now every time I run this, the distribution will be slightly different because these are generated using random numbers. Okay, you can see that distribution is changing. All right, so this is the bin. Okay, so there are other this one also, there are other parameters also. One parameter that I'm interested in is the R width. R width is the relative width of the bar as a fraction of the bin width. The relative width of the bar as a fraction of the bin width. So I'll tell you what this means. Okay, let me add one more slide. So let us say this is my bin. I'll draw a line here. This is the bin. Okay. Okay, so this is the bin. So now I want to plot a bar here. Let me get this below. I want to plot a bar here. What has happened here is the bar that I have drawn, let me bring it, put it below. The bar that I have drawn, the size of the bar, the width of the bar, and the size of the bin, they're matching. The bar has completely filled up the bin. The bar has completely filled up the bin. So here, this is in this example. Okay, in this example, what I have drawn over here, the value of this parameter R width, the value of this parameter is 1, which is the default value. R width is equal to 1.0. So it means that the bar has completely covered up the entire bin, 100%. 100% of the bin has been covered by the bar. But let's say I want to change that. Okay, I want the bar to cover only 90%. So if I make this 0.9, 90% means 0.9, then what will happen is the bar size now the width of the bar will now reduce. It will now become 90% of the size of the bin. Okay, so you could choose to place the placement of the bin, whether it's on the left side, whether it's going to be on from it the bin will it be drawn, the bar will it be drawn from the left edge, will it be drawn from the right edge, okay, will it be drawn right somewhere in the middle. Okay, so that you can control. Okay, that you can control. So but right now we know that the width of the bin, it has become 90%. You could change this even more. You could change this even more. Let's say I make it 50, 0.5. Then what is going to happen is the bar size is going to become exactly half of the bin size. is going to become exactly half of the bin size. So R width is going to basically control that. And by having a good value of R width, you will be able to see the gaps. Now what's happening is, this is one bin. When we're having, R width is equal to 100%, you're having one bin. R width is, by default it is 1. So this is one bin. Now let's say we have the next bin. I bring the next bin. Okay, this is where the next bin is going to be. There is no space, there is no gap between the first bin and the second bin. Let's say this is the next bin. There is no gap between the first bin and the second bin. So that's why we are not able to see any spacing between them. But now let's say I make another copy of this one. Let me delete this. Now, so the bins will be always side to side. The bin will be side to side. With R width is equal to 90%. Okay, with R width equal to 90%. Now you can see that there is a nice gap between the two bins. This is the first bin and this, let's say, the second bin. Now you'll be able to see the difference between where the different bins are, the different bars are. So you can do that using the R width. Okay, so you can change this. So let me just change this here. So I'll add this parameter R width. Let's make it as 0.9, 90%. You can see the gaps here. Now it's looking little like this because of something called as anti-aliasing. Okay, there's something called as anti-aliasing in signal processing. That's why we are getting some patches here. But if you save this as an image and you open this, it will look perfectly fine. Okay, so let me just save this as an image. Okay, I'll make DPI 300. You can see here, we're able to see the gaps nicely. Okay, they're nicely going to be spaced. Okay, so this is plotting histogram. Okay, just play around with this. Any questions? Any questions so far? Okay, so I'll go to the last topic, which is 3D surface plot. Okay, then after that I'll just show you some applications, some real applications. This 3D surface plot. So I have just taken this from this tutorial. Lots of tutorials are available. I've just taken the code from here and I've used it, I think somewhere here. Lots of different kind of surface plots you can do. Everything is available for free. Okay, so this is the plot. Okay, this is the plot that we'll be doing here. So this is the function. Okay, sine of under root x square plus y square. Sine of under root x square plus y square is the function. The function is z of x comma y is equal to sine of square root of x square plus y square. X square plus y square. This is a very popular function which is used everywhere on the internet for for giving lots of different kinds of demo. It is used. Okay, so this is the function that we are trying to plot over here. So this function definition, it does that. It calculates, given the value of x and y, you pass x and y as the arguments, it will calculate and it will give you the value of z. So we have to create, first of all, whenever you're doing surface plot, you have to do something called as a mesh grid. Okay, what is a mesh grid? Mesh grid is basically this. Let me go back to the slide and show you here. So we have a set of values. Okay, we have a set of values for x. Okay, let's say these are the set of values for x. Let's make it thicker. So this is, let's say this is one x value. I'll just give a simple example. This one x value. Then let's say this is another x value. This is another x value. This is another x value. We'll just take these values. Okay, so this is our x. Okay, now correspondingly we have a set of y values. Correspondingly we have a set of y values. Let me just copy this. Let's say I'll keep this as the same. So these are a set of x values. Correspondingly we have set of y values also. Similar to this, for each x there is a value of y. Okay, there's a value of y. So when you plot this, a 2D plot, you're basically plotting these set of coordinates. Now I don't want to plot this in 2 dimensions. I want to plot a surface plot. So I have a scenario where some other function is depending on combinations of x and y. So here, whenever you're doing a 2D plot, you're just combining this. You're just having this coordinate, this coordinate, this set of coordinate, and so on. But in 3D plot, you have to consider each and every pairs of values. So you have to take this x and this x. You have to find out this x. We have to take a combination with this y, this y, this y, this y, and this y. You have to take all possible values of y and get the combination. So let's say this is x1, x2, x3, x4, x5. So we need to calculate the value of the function at x1, y1, x1, y2, x1, y3, x1, y4, and x1, y5. Similarly, you have to calculate the value of the function at x2, y1, x2, y2, x2, y3, x2, y4, x2, y5. Okay, so that's what we have to do. So how do I get these combinations? How do I get these combinations of x and y? The way to get these combinations x and y is by using what is known as a mesh grid. Okay, we use something called as a mesh grid. So what we do is you take these x values, okay, you take these x values and you take the y values and you create all possible combinations. Okay, and that set of combinations, another way to visualize that set of combinations would be something like this. I'll make it smaller, don't worry. Okay. So I have rotated this y, okay, by 90 degrees. I have rotated this y. Now what we need to do is we just need to take intersections of these. So this is your, sorry, we use the x values first. So you take this value of x, okay, you take this value of x. Similarly, you take the other value of x also. So this is one value of x, then another value of x. Next one. In a similar way, we take the y values. We select each and every value of y. Okay, so now you can see here, wherever there is an intersection, wherever there is an intersection, that is, for example, here, okay, and here, let's say this one, this is another point of intersection. This is another point of intersection. This is another point of intersection. Okay, you see these points of intersection. All of these points, this point will give me the combination of this x and this y. Similarly, this point will give me the combination of this x and this y. This point will give me a combination of this x and this y. This point will give me a combination of this x and this y. So we are basically creating these huge combinations of x and y. Okay, and once we get this huge combination of x and y, we can now just calculate the function at each and every of these points. So let me just, for the sake of completion, let me just put these also. Similarly here. And similarly here also. So this is what is meant by a mesh grid. So we started with a array of x and we started with an array of y. Using this array of x and y, we have got various different, all possible combinations of x and y. So all these possible combinations of x and y. So for instance, let's say this point, let's say is xi. Okay, this point, let's say is xi. And similarly, let's say this point is yj, let's say. This point is this point is yj. Then the intersection of these two, will be xi. The intersection of these two will be this point, and this point is that tuple xi comma yj. Okay, so this is what is meant by a mesh grid. So it is going to give us this combination of xi's and yj's. So now you can just use this xi and yj's in that function, in this function. You can use in this function, and that is going to give you the value of this function at this particular point. Okay, so we are basically sampling in space here. So this is what the mesh grid does. Mesh grid, it creates this set of x and y values. Okay, it creates this set of x and y values. Then now again, we create a figure, then in this figure, we create an axis. Okay, we have to do it this way. Okay, and we have to give in this axis, plt.axis, we have to give this argument we have to pass, projection equal to 3D, because we are drawing a 3D projection. And then we create a variable called the surf. What this surf is going to do is it's going to plot surface. Okay, it's going to do a surface plot. The command for doing the surface plot is plot surface. It takes x and y, which we got from the, not these x and y, not the small x and small y, not the arrays, the x and y that we got from the mesh grid, the combinations. Okay, so x and y, and then we'll take z, x comma y. So because you see, what is z? Z is this function. Z is this function. So it will just substitute whatever are the x and y values combination in this mesh grid. It will just put this in this function. So that is going to return the corresponding values of z at each and every point on the mesh grid. Okay. Let me just keep it as binary. Edge color is none, and then figure color bar. This surface. Okay, whatever is the surface, I just put show some kind of a color bar over here, and then you can just show the plot. Okay, so once you do that, we have a plot like this. Okay, but this one is it's black and white, it's gray, because I have used there are lots of different color maps available. So this is because the color map is binary. You have lots of other color maps also. So cool is there, then it's going to give shades of blue. Then you could have heat color map, shades of, no, I think it's hot. Yeah, so we have these shades of red and orange and so on. So this and this command, This color bar, it plots the color, it plots the color bar. So just by looking at the color, you know what is the kind of value that we have at that point, okay, on this mesh grid. What is the value that this your Z is taking at that point on the mesh grid. So that's how you can do the surface plot. So I'll not do any more, and you can actually just explore this page, which I have given here, and you can just try out all of these different plots. You can have parametric plots also. So suppose I have a body which is moving in 3 dimensions, right? You could, if there's a parameter which can define its motion, you could have a parametric curve like this. So you could demonstrate planetary motion. You can have, because if you've done classical mechanics, you know that planetary motion of a planet, of a satellite around a planet, or the planet around a star, you can actually parameterize this. So you can have a parametric curve, and over there you can actually show the orbits of a planet going around, let's say the sun, let's say Earth going around the sun. You could display the orbit in plots like this. So you can try this out. Okay, just I'm throwing ideas. It's totally up to you how you'd like to go ahead with this. So that's about all the things that I wanted to show you about having different kinds of plots. Then I'll just show you an example. Okay, one example is smoothing of plots. You can actually smoothen plots and make it look better. This I have used a file called as sunspots.dat. It's there in that day2 folder. The day2 folder, that this file is already there. Okay, it contains data regarding the number of sunspots. Okay, the sun has been observed like since 1749. Okay, the sun has been observed. The number of sunspots that is observed on the sun. Okay, this file, it contains all that data. Okay, then for every month. Okay, so we have 2 columns. The first column is the month, and the second column is the number of observed sunspots. So we have to write a program which reads the data and plots the graph of number of sunspots versus time. So because the number of sunspot, it changes, it varies from month to month, it varies. So we can write a program which can read the data from this and plot this. Okay, and then we modify the program to display only the first 1000 data points. That is easy. And lastly, we will try to make this plot a little bit smooth by using this function. Okay, so first let's go ahead and I'll show you just the plot, the sunspots. Okay, so this is the sunspot data. You can see here from 1749, okay, till I think 2012 or something. These are the sunspot data. You can see the number of sunspot, it periodically increases and decreases. Okay, the number of sunspots. Let's make it a smooth curve. Okay, line width, let me change this a little bit. Let me reduce. Line width is equal to 2. No, it's too much. Okay, so this is how the sunspot data looks like. Okay, now see, you can see a lot of fluctuations over here. You can see a lot of fluctuations over here. So let me just save this figure, then you will be able to see this better. plt.savefig. Data.png. DPI is equal to, let's say, 300. The file should be saved here. Yeah. Okay, so you can see here there's a lot of fluctuation. Okay, very large amount of fluctuation. So one way by which you can reduce these fluctuations, is by smoothing the data. So what you do is, we have lots of different points. So we'll take certain number of points. Okay, we'll take certain number of points. So suppose I have one single point. I take 5 points this side, 5 points the other side, and then I find out what is the average value, and then I replace that point with that average value. So we find some kind of an average here. Okay, and this is what is being done in this case. So we take certain number of points. We take certain number of points, 5. Let's say 5 points I have taken. 5 points means 1 point at the center and 2 points to the left, 2 points to the right. Okay, 2 months to the left. So because every point represents a month, so you take any 1 month number of sunspots, then you take, total is 5. So 2 points to the left, that means 2 months to the left and 2 months to the right. So we find out the average value. This kind of an average we calculate. Okay, we calculate this kind of an average, and then what we do is, that single month, whichever I have chosen, it will be replaced with the value will be replaced with at that point will be replaced by the value which is given by this average. So this way you can actually smoothen this one. So let me show you the smoothened curve. This is in black. This is smoothened. Okay, so this one I'm using 5 points. Okay, I'm using 5 points. You can see the difference. Okay, the magenta line, that was the original plot. There were a lot of fluctuations. So what I did was every point I have replaced it with its average. So you can see that the plot has become a little bit more smoother. The fluctuations, the big fluctuations, they have now reduced. The fluctuations, they're all gone. I mean, they're still there, but still it has become more or less smooth. Now I can, because if I consider this one, the original one, and if I do some kind of a Fourier transform, you'll find a very high frequency noise here because of the irregularities, very high frequency noise. But if I do the same analysis here, then I'll be able to find the frequency much better because the noise has gone. I have smoothened out the noise here. Okay, I can show you some more. Let's say I take, instead of 5, let's say I take 15. Okay, 15 points. Okay, so instead of 5 points, I take, let's say, 15 points. It got even smoother. This was the original data set. This is using 5 points. I have smoothed using 5 points. This is using 15 points. So it has become even more smooth. Okay, so you can do these smoothing of curves. You can do that using Python. Okay, so I encourage you to go through this code, and then it will give you an idea as to how this has worked, how I have been able to do this. Okay, very straightforward. Okay, I've not used anything new, just whatever concepts that we have learned so far, everything is the same thing. Then scatter plots. Yeah, this is an interesting kind of a plot. It's called a scatter plot. Sometimes we want to plot data which are not dependent. Okay, so this here I'm having, along the x-axis we have time, along the y-axis we have number of sunspots. So number of sunspots obviously depends on time. Okay, so we have a independent variable along the horizontal and a dependent variable along the vertical. But sometimes we don't want to plot dependent. We want to plot variables which have very less correlation with each other. So in that case, scatter plots will be really good, a very good way of doing that. So one example is something known as a Hertzsprung-Russell diagram. Those who are into astrophysics, you'll know about this. Okay, Hertzsprung-Russell diagram, it's basically a plot of luminosity versus temperature. Luminosity along the y-axis and temperature along the x-axis. Only thing is, it decreases from left to right, it decreases, and from bottom to top also, it decreases. Both the luminosity and the temperature. Okay, that's the Hertzsprung-Russell diagram. So the data for this diagram, it is stored in stellar.dat file. Okay, now it is luminosity versus temperature. Now temperature and luminosity, they all depend on other things. They all depend on things like the mass of the star, they depend on the radius of the star. That's what they depend on. So temperature does not depend on luminosity. Direct temperature has a correlation with luminosity, but it does not depend on the luminosity. So temperature and luminosity, they are two independent variables. They depend on something else. So now this will be a good place where I can actually use a scatter plot. So you can read more about scatter plots from this link which I have provided over here. For now, I'll just show you the demo. Okay, so what we need to do is, again, I read the data. Okay, I read the data using that np.load text. Then first column is the temperature. So I use slicing. To extract the first column. Second column is the magnitude, which is basically the luminosity. So I use slicing to extract the magnitude. So temperature will be along the x-axis and magnitude will be along the y-axis. Okay, so then let me just hide all of these. Okay, so now we plot. Okay, temperature along the x-axis, the luminosity or the magnitude along the y-axis. The color is blue. Alpha, I'll tell you what this alpha is. Let's just go to it one by one. Go through this one by one. First, we'll just do the basic plot, which we are already familiar with. Okay, so this is what we got. Okay, let me just save this also. plt dot savefig. The name of this, let's say HR diagram.png, dpi is equal to 300. Okay, let's just plot this. Okay, so we have this here, which is, where is this? Here it is. Okay, this is the HR diagram. Okay, now you can see here every single point. Okay, every circle represents one star. Every circle represents a star. Okay, you can see lots of stars over here. You can see this is how it goes. So this way temperature is increasing, and this way that the luminosity, the magnitude is increasing this way. So we have this, but like I told you, it's not plotted this way, right? It's plotted the other way around. Okay, it's plotted in the opposite direction. What happens is the temperature from left to right, the temperature actually decreases. From bottom to top, the luminosity decreases. Okay, so how do I do that? How do I flip this? How do I make the temperature from here? Usually when we plot, it is from left to right. The left to right is, it's increasing, it's going from decreasing from a small values, it goes to higher values. But how do I decrease the temperature? Very simple. Along the this one x limb, we'll just flip the values. X limb, we'll put the highest values and we'll put the lowest value, which is 0. The highest value first, lowest value 0. So this way it is going to flip the x-axis. Okay, it has now flipped the x-axis. Now I want to flip the y-axis. Again, the same thing. I know the maximum minimum just by looking at the data. I knew what was the maximum minimum. Maximum was 20, minimum was -5. So I just flipped it. I first put 20, then I put -5. So it will start from 20 and it will go to -5. Okay, so this is how it is supposed to look like. Okay, so that's the Hertzsprung-Russell diagram. So now what we do is we put the labels here. Okay, y label and the x label is going to put the magnitude and the temperature. Now next thing is, you see, this is, I find this plot to be very distracting, because you see I'm not able to see they all have because every point represents one star. Every point represents one star, but here in this place, in somewhere over here, these stars, they've got mixed up. So I have absolutely no idea what kind of density we are having. It's like as if this could be lots of stars, but I don't have any idea of where is the density of stars more, where is the density of stars less. I have no idea. So for that, what we can do is we can change the opacity of the circles. Okay, by changing opacity, this is what I mean. Okay, so let's say I have a circle. Okay, let's say this is a circle. So I could change the opacity of this circle. I think I can do it here. No. Yeah. So I want to change the opacity. Let's put something else also below. Let me see. Let's say I put some other. Let me just make a copy of this and paste it here. I'll remove the line. Okay, so one more copy of this. Okay, so I really have no idea, right? Where is the density more, where is the density less? It's just looking like one blob, right? One irregularly shaped blob, that's what it's looking like. One irregular shaped blob, that's what it's looking like. So I have no idea where it is more dense, where it is less dense. So what I can do is I could play around with the opacity. So I could make it more transparent. Okay, so right now the transparency is 0. I could make it more transparent. Okay, I make it, let's say 50%, or let's say I make it 70%. Okay, this is too much. Let's make it 30%. Okay, likewise I do for the others also. I make it 30% for this, and for this also I make it 30%. So basically you're making the circles, you're making them transparent. So you can see now if you move them around, you can see where the density is more, because obviously this place is most dense, because here the shading, it is the darkest. The density is least over here. Okay, so you can do that. This transparency, okay, this transparency, you can actually control it. The transparency or the opacity, in other words, that's another way to look at it. This transparency or the opacity can be controlled by the there's a parameter called alpha. This alpha parameter can control Okay, this alpha parameter, it can control whether it's going to be more, how transparent or opaque it can be. Okay, so this alpha parameter is given over here. So you just put one more parameter inside scatter. We put alpha. Alpha is equal to, let's say I put 0.2 over here. Now when you run this, you can see now this is much better. Okay, now you can see very easily the kind of densities that we have here. It obviously looks like there's, you know, more density here, and towards the edges we have, you know, lesser number of stars, right? So it looks, it's giving me a more accurate picture. You could just play around with this alpha. Let's say if I make it as, let's say 50%. No, let's make it, because there are too many data points, that's why. Let's say 10%. Okay, it's become even faint. But if you have, you know, if you make it too small, you'll not be able to see some of these circles also. So that also we have to take into account. So you can play around with the opacity in this way, and then you can change the marker. Marker is equal to O. Okay, just circles. So this is your scatter plot for HR diagrams. Okay, let's give it as 0.2. Okay, so that's about making scatter plots. Then we have density plots. Density plots is generally, suppose I am having two independent quantities. Okay, two independent quantities, just like let's say X and Y. I showed you that mesh grid, no? I showed you that mesh grid here. X and Y, these are two independent quantities, and we have one more quantity which depends on this. Okay, which depends on this. There are many ways to plot that. You could have a surface plot, just like I showed over here. Another alternative to the surface plot is something known as a density plot. Something known as a density plot. Instead of using the surface, what we'll do is we can use some kind of colors to actually show the variation. Okay, so that is done by using what is known as imshow. It is done by using a function called as imshow. It basically creates an image, because after all, images, they're basically matrices only. You have a what is an image after all? You have a mesh grid. Image is a photograph. Photograph is basically a mesh grid like this. At different points we have different values. 0 means black, white means let's say 255, right? So putting different values of, you know, different values from 0 to 255, we can get the whites and the blacks and the different shades of gray. So that is going to give an image. So basically that's what the imshow does. I am image show. Okay, so that gives us what is known as a density plot. So I'll get the data. There's a file called as circular.dat. Okay, this circular.dat, it contains data for, circular data which you get from circular fringes. Okay, it's all available. You can just load this and see. So you just get the data, and then you don't have to extract X and Y. You can just directly give the data to it. It contains 2 columns. It will directly use that. It contains 3 columns actually, and it will directly use these 3 columns to create this image. I can show you here. Okay, so this is a density plot. So here the colors, they have a meaning. So this means, maybe this yellow means a high value, this blue means a low value. Okay, so now generally we don't plot this like this. Okay, you can see the origin here. Origin is at the top left. Okay, this is the x-axis, origin is here, and the y-axis, origin is here. So you are plotting the origin at the top left, but we don't want that. So if you want to get the origin to the bottom left, so to get the origin to the bottom left, you just pass one more argument, imshow data, origin is equal to lower. It is going to bring this to the bottom left. Now, generally it's better to show using grayscale, because we have really no idea as to what this kind of color map is. So for that, what you do is before the show, you will just call plt.gray. So it is going to convert that into a gray image. And this is what is going to get. You're going to get black and white. So now just by looking at it, you know that here somewhere at this point the value is maximum. At this point the value becomes minimum. Okay, so we have maxima and minima like this. So that is your density plots. And lastly, one more example. This is one that I have done here using, this is interference of waves. These kind of diagrams you would have probably seen in your physics textbook, undergraduate physics textbook, and maybe in your higher secondary also, you would have seen diagrams like this. So basically the idea is, suppose I'm having particles on a water surface, and then you make it oscillate. Okay, then what is going to happen is it's going to create waves. Okay, and those waves, they are going to superpose at any point using the superposition principle. This is the superposition principle. Okay, so you can find out the superposition principle. So at any point, okay, if the center, suppose center of the circle from where you're making the disturbance, if the center is x1, y1, that any point, the distance to that point is given by r1, which is under root x minus x1 whole square plus xy minus y1 whole square. Okay, and the height of the wave is given by this, some amplitude into sine of, it depends only on the distance, sine of, it depends only on the distance from the origin. So likewise, you could have another point. Okay, you could have another point. Okay, this is not r1, this is r2. We have another point which is r2. Okay, so another point r2, which also has, whose position is like this, and it is going to create a sinusoidal ripple, and the sinusoidal ripple is given by this. So at any point, point, because now I am having two sources of disturbance, these two sources of disturbance will create this. The first source will create this wave, and the second source will create this wave at all points. Now, if I want to find out what is the disturbance at any one point, I have to do a superposition of these two waves. Okay, in this superposition, I can actually use a density plot to show how the superposition is actually taking place. So here, well, I'll just go through this line one by one. So wavelength I have chosen to be 4. So wave number, okay, angular wave number, so twice 2 pi by wavelength. Okay, so initial, this x0 is 0.5, x0 is 0.5, and the separation, okay, separation between the 2 points, the separation between the 2 points is 16. Then side of length 100. I think these are some things that I have taken from here. Okay, display the same over a 1 meter square region, 1 meter square region. So the side, we are taking a square, side of the square, the area of the square is 1 meter square. That means side of any one side, it will be 100 centimeters. Okay, so now I have taken 500 points, 500 grid points on each side. It's like this. 500 points along x and 500 points along y. Okay, 500 points here, 500 points here. So 500 into 500, those many number of grid points will be here. So once we get this, now we can find out the spacing. What is the spacing between points? Spacing between points will be, what is the side? 1 meter, and in 1 meter there are 500 points. So the spacing between points will be 1 meter divided by 500, or 100 centimeters divided by 500 points. So we just find out. Okay, so x1 will be side divided by 2, half of the side, because I want to locate, I want to put these 2 points right at the center. Okay, one, suppose I have a box, I want to put both these points, the disturbance, I want to put them right at the center. So half of the side and half of the separation. Similarly, y1 will be half of the side, and x2 similarly over here. This is going to locate the positions of the centers of the circles. So then what we do is we create one more array which will store the height. So it's just an empty array which will store the heights of the waves. So now what we do is we go over all these points. Okay, we go over all these points. Okay, we have 100 points. We go through each of these points. Then we construct the y values. Okay, we construct the y values, and then over again we go one more, because we have to go both x direction and y direction. X will be equal to spacing into j. Okay, x will be spacing into j. J is this, is the iteration variable. So x will be, first will be at 0, then it will be whatever, 1 spacing, then 2 spacing, then 3 spacing, and so on. This line is going to do that. Then r1, we find out what is the position of that point with respect to the first point. Then we find out r2, what is the position of that point with respect to the second point. Then after that, we just calculate xij will simply be, we just use this formula. Okay, chi naught, x naught. Okay, sine, because x naught is the amplitude here. Okay, I made a mistake here. X naught is the amplitude. Okay, that's what it says. Amplitude is 0.5. I'm calling this chi naught. I'm calling it as x naught here. Then what you do is you just calculate using this formula. As you can confirm, this is the same formula. X naught sine k r1. So it's chi naught sine k r1 plus chi naught sine k r2. I'm calling it as x naught sine k r1 plus x naught sine k r2. Once we have got this, then you can just use imshow. You can use imshow, and using this imshow, you can plot this. Okay, let me show you this. There is a grayscale. So this is the kind of distribution. This is the kind of when we have, so 1 point, x1 is here, x2 is here, and then these are the places where you have this constructive and destructive interference wherever it's taking place because of the ripples. These white ones are the places where constructive interference is taking place, and these gray ones are the places where destructive interference is taking place. So you could have a computation and combine that with ImShow to give you a plot like this. Okay, so that's about your visualization using Python. If anybody has any questions, you may ask. Otherwise, maybe we can take a 5 minutes break, and after that, I'll go to the last topic, which is basically whatever Samrat had done yesterday. The Newton-Raphson and the bisection method, all of these. This is a demonstration of how you can go about doing that in Python. So if you have any questions, you may ask me now, or you can take a break. Samrat, are you there? Yeah. So what do we do?
Yes.
Shall we take a break? Quick break, maybe 2 to 3 minutes?
Yes. 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 We can take a quick break.
Okay, it's 12:16. Let's meet at 12:20. We'll continue at 12:20 after 4 minutes. Okay, can we continue now?
Yes, let's continue.
Let me know if you're able to see my screen.
Yes.
Okay, so in this lecture, we'll just be looking at some numerical analysis using Python. First is the root finding. This was already done yesterday. The theory behind this was done by Samrat yesterday. I'll just use some of the slides which I had used in another workshop in 2018. It was workshop on numerical methods using spreadsheets. So over there, I had done the same thing, but I had used spreadsheets for that. So I'll just use the formulas from here and just to correlate this over here. Okay. So let's say I have a function. Okay, I have a function f of x equal to x square minus 5x plus 1. I want to find out the roots. So when you look at this function, this is a quadratic function. Okay, so a quadratic polynomial is on the right hand side. So when you try to find out the roots, it will give you two roots. Okay, so we are familiar with that. So first we'll look at the bisection method. Okay, so what do you do in bisection method? Just to recap what Samrat had told yesterday, bisection method is what you do is you start from 2 points. You start having two guesses, right? So you have to, if the root happens to be in between the two guesses. So we have one guess, another guess, x0 and x1. Then this is your starting search interval. Okay, so what you do next is you just bisect this. You divide this by 2, and then you find out the midpoint. Then you have to check, okay, the value of the function at that midpoint. If the value of the function, okay, at that midpoint, it's having the same sign, okay, to whichever, okay, on both sides, I'm find out the value of the function. By the way, this function, the way, how do you check whether your initial guess is correct or wrong? Because you see, if it is a root, that means it has crossed the x-axis. Cross the x-axis means on one side it will be positive, on one side it's positive, on one other side it's negative. So this is how you can check. Just when the guess is given to you, you first check what is the value of the function at those two guess values. Find out what is the value of the function at x0, and then find out what is the value of the function at x1. If x0 and x1, you take the product of them. Okay, x0 and x1, you take the product of them. If the product of the function f of x0 and f of x1, if the product of these two functions at these 2 points, if it is negative, then that means it's a correct guess that we have chosen. Because suppose I have chosen x0 and x1 here, x0 was here, x1 was here, then both the function is positive. The function is having positive value at both the guess values. Then if I take the product of two positive values, it is going to be positive. So that means that is not a good guess. Similarly, if both are on the negative side, the function is having negative value on both the guess values. So as a result, the product of two negative will again give me positive. So you need to find out what is fx0 times fx1. If that quantity is negative, that means it's a correct guess. So that is what we will also test, we'll use to test. Okay, so then you find out the midpoint. Then you check the value of the function at this midpoint, the value of the function at this midpoint, and the value of the function say at x1. If this product, if the product happens to be positive, if the product happens to be positive, that means the midpoint and x1, they happen to be on the same side. Then x1 this will become the new x1. The midpoint that is going to become the new x1. Okay. If not, then x naught will become the, sorry, this midpoint will become the new x naught, and then you shift this over here, and then you bisect this again. So keep on repeating this until you reach some kind of tolerance. The difference between the present guess and the present estimate and the previous guess, the difference between them, if it is smaller than some tolerance level, which we call as epsilon. Okay, if it is less than some tolerance level, that's where we will stop. Okay, so we can do that. Let's say this is an example that we have seen over here, that I have put over here. So the function that is being considered is x square minus 5x plus 1. X square minus 5x plus 1. You can change the function, the way the function looks, you can change it over here. X square minus 5x plus 1. So whatever value of x is put, it just calculates this one and returns this. So I defined a function called as bisection. Okay, I defined a function called as bisection. This is going to do the job for me. It is going to do the iterations for me, and it's going to show you each and every step what is happening. Then what are the arguments? The arguments are A and B. And what is A and B? A and B I'm taking from the user. A is the first guess and B is the second guess. So you apply the first guess and the second guess. You can also obtain the epsilon value, the tolerance from the user, but right now I'm just keeping it as 10 to the power minus 6. Okay, 1 micron. Okay, micro that I'm taking it as the epsilon value, 10 to the power minus 6. Okay, so I'm just keeping it constant. You can change this also. You can make it, you can allow the user to enter this also. So we have the first guess and the second guess, first guess and the second guess. And then I have also put epsilon as the third parameter, but you can see here, I'm keeping this as a default parameter. Epsilon, I'm keeping it as a default parameter. So that means even if you don't pass on the value of epsilon, doesn't matter. It is just going to use 1 into 10 to the power minus 6. So then these are the two starting points, x low and x high. The lower value and the upper value. Okay, the lower value and the upper value, the low and the high values. These are A and B. Then what you do is you just print out, because I want to show this as a table. We just print out. We do the serial number, then we print out the x low, then x high, then the value of the midpoint. C is the value of the midpoint, and the value of the function at the midpoint. Okay, then I create a variable called as I. This is going to keep track of the number of iterations that we have here. Then what we'll do is we will check if the difference between these two, if the difference between these two values is greater than or equal to epsilon or not. Okay, that is these two, this x0 and x1, okay, x low and x high. We'll first check if the difference between these two, if the difference between x low and x high beginning itself, if this difference, is it less than epsilon or not? If it is less than epsilon, then we don't have to worry about it, because both the guesses, they are very close, right? So there is no point going through this one. So this loop is going to be executed so long as the difference between them is greater than epsilon. Okay, because remember, we are doing numerical computations. You cannot have exactly value any quantity becoming exactly equal to 0. Okay, there will be some kind of a approximation. So that's why we have to have some kind of a tolerance. So the difference, the absolute value, okay, this finds out the absolute value, the difference between the two guess values, as long as it remains greater than epsilon, then execute this. Then this finds the midpoint. C is the midpoint. How do you find out midpoint? Just add both of them and divide by 2. x0 plus x1 divided by 2. x low plus x high divided by 2. Once you have found out the midpoint, then you find out what is the value of the function at the midpoint. Okay, what is the value of the function at the midpoint? You got the midpoint, you find out what is the value of the function at the midpoint. That is going to be y. Okay, once that is done, then you print it out, whatever values you have got. The iteration, the value of the iteration, which number of iteration it is, what is the x low value, current value of x low, what is the current value of x high, what is the midpoint that I got, and what is the value of the function at that point. Okay, so what should happen is, as this iteration proceeds, the value of the function, it should become smaller and smaller, and it should become close to 0. Then I increase the iteration, because now we are going to the next iteration. But before we go to the next iteration, we will have to also do some kind of checks here. The check is, if the absolute value of y, if the absolute value of the function is extremely small, because remember, what are we trying to do? We are trying to find out the roots. We're trying to find out the roots. Root means the value of the function becomes 0, but you can never have value reaching exactly 0. So what we will do is, we'll check if this function, this height, this vertical line that you see, is this height, is it small enough? Is it small enough? Is it really close to the this x-axis? If this is very close to the x-axis, that means we are reaching almost the root. Okay, so if it is less than epsilon, we need not proceed. We can just come out of the loop and we just return whatever is the value of c, that itself will be the root. Okay, then else, if this is the logic part, this is how you set the next value of x low and x high. Else, what we do is we multiply the value of the function, at the midpoint, you multiply with the value of the function at the low point. If this is positive, that means, if this is positive, that means x low and the midpoint, they are on the same side of the root. That means x low will become the new midpoint, that is going to become the new x low. The midpoint is going to become the next new x low. Otherwise, the midpoint will become the next x high. And you run this. So this is going to return. This is going to return the value of c, and that value of c will be the estimate of the root. It is not exactly the root, it is going to be the estimate of the root. So in the function, in the program, what you do is we take from the user A and B, the initial and the starting and the first and the second guess. Then we set the epsilon value. You can take the epsilon from the user. If you want to do that, you just have to remove this comment and put a comment over here. Okay, but I choose to keep it like this. Then first thing that we need to do is before calling this bisection function, we have to check whether the guess that you have given, whether it is a good guess or not. You have to check that. And how do you do that? I already told you the two points, they should not lie on the same side of the root. How do you check? Just find out the product of the functions at both these 2 points. If they are on the same side, then the product of the functions will be positive. So you first check that. If the product of the functions at the two guesses, if it is positive, then you just print out that root finding using these values is not possible. Then you have to try this again. Okay. Else if if the value of the function, it becomes very small, the value of the function at A, okay, you have chosen one guess. Another possibility is the low value that we have chosen. That low value could be very close to the root. You could have maybe by stroke of luck, let's say you have chosen this one, the low value to be extremely close to the root. If you have chosen the low value to be extremely close to the root, how do you check? You find out what is the value of the function, okay, at the low value. If the value of the function is less than epsilon, that means it is also a good estimate. So you can just say the first guess value is an acceptable estimate of the root, hence the root is A. Okay, next, the same thing you can apply to this. By chance, let's say this second guess, if it is very close to the root, the same thing. If it is the value of the function at the second guess, if it is less than epsilon, then you can just say the second guess value is the acceptable estimate of the root, and hence the root is this. So using these if else conditions, these ones, they actually prevent, I mean, a lot of this one, you don't directly go and perform the bisection. Just do these initial checks first. Once none of these are true, okay, then you can go ahead and you can do the bisection. So it is going to find, so this function is going to find out the root and it is going to return the root, and then you just print it out that using the bisection method, the root has been estimated to be so and so. Then you can plot this. Okay, you can plot this. I'll just hide these two to show you this. So you can just plot this to show that the result that you have got, whether it's correct or wrong. Let me run this now. Okay, first guess. Let's take the first guess to be 5 and 9. Okay, finding root using these guess values is not possible. Okay, so I should have used exit from here. Let's see, XIT, no. I have to, for exit, I have to use that OS package. Okay, I'll not do that. Okay, exit package. But we know that the guess values, these are not good guess values. That's the idea that I got. Okay, this is, we got the guess value is not, it's not a good guess value. Okay, all right. So let's run this again. Let's try a different set of guess values. Let us say I use -10 and let's say 2. I do this. Yes, it has been able to do this. So this is a good guess value because I did not get this message. Then neither -10 nor 2, none of them are close to the root. So these two are not did not get executed. So what has happened is the bisection method that has got executed because I'm able to see this these values here. So your starting value, okay, x flow is -10. I have chosen -10 here. X flow, I have given -10. Okay, so -10 is the x flow, and the second guess is 2. Okay, so the midpoint between -10 and 2, the midpoint is -4. The value of the function is 37 at that point. Okay, then what has happened is it has taken 2. A higher value has remained the same because you see this is -4, so this -4 will come over here. It has checked the condition. So like that, it keeps on doing this, and you can see progressively the value of the function is going on decreasing, right? Even though it's showing 0, 0, but there are other decimal. I'm not showing the higher decimal places. At the 22nd iteration, it becomes finally less than 10 to the power -6, and then we say that we have estimated the root to be 0.209. So this is one iteration. So we have found one root. This is this root. Okay, now it'll be nice if we can actually show this root. How do you show the root? One way to do that will be just draw a horizontal line and a vertical line. At the root, you draw a horizontal and vertical line, which is at the intersection. Their intersection is at the root. So to do that, I just added these two lines of code. Okay, you will, I mean, just look at this. You'll figure out for yourself what this line does. Let me run this again. I'll use the same ones, -10 and 2. You can see it has drawn a vertical line which passes through 0. Okay, now you can draw a horizontal line also. The second code, it does that. It draws a horizontal line through the root. So -10, again 2, same number of iterations. So you can see this cursor, wherever it's intersecting, that is the root. Okay, so this is one root. What about the other root? The other root, it seems to be somewhere between 4. This is 2, 3, 4, 5, and 6. Somewhere between 4 and 6. Somewhere between 4 and 6, we have the next root. So let's run this. Let's try to find out the next root. Okay, so what you can do is somewhere between, the root lies somewhere between 4 and 6. So if it lies somewhere between 4 and 6, that means we can choose, let's say, 2 and 10. Okay, we can choose 2 and 10 as our starting guess values, +2 and +10. So 2 and 10, we start as the one. So it has done this. So it has found out that the root is to be 4.791, and it has indicated that also using these vertical and horizontal lines, that what we have got is indeed correct. Okay, so this is your bisection method. Next, Newton-Raphson method. Again, Newton-Raphson method, you have done the theory behind this. So Newton-Raphson method is this. So in the Newton-Raphson method, what you have to do is, you don't have two guesses, you just have one guess. Okay, then at this one guess, you find out what is the slope of this function. Okay, then you draw a line, and that line, wherever it intersects the x-axis, okay, that becomes the new point. Okay, again you find out the value of the function, find out the slope at that point. Again you find out the next point. Again, progressively you are getting closer and closer to the root. Okay, so in general, if you have xi, how to go to the next one, xi plus 1. If you know xi, how to go to the next I plus 1, all you have to do is just xi minus the value of the function at xi divided by the value of the derivative of the function. So x0, what is x1? x1 is equal to, x1 will be equal to x0 minus the value of the function at x0 divided by the value of the derivative at x0. Okay, similarly, once we got x1, how do you get x2? x2 is x1 minus the value of the function at x1 divided by the value of the derivative of the function at x1. So you need the derivative also in this case. So that's the Newton-Raphson method. So here, the same function, I've used the same function just to show that the roots, we are able to get the roots here. Just I want you to see the number of iterations. Okay, in Newton-Raphson, as Samrat had mentioned yesterday, it's much faster. Okay, we want to verify if that's indeed the case. So I have chosen in this case 2 and 10, and the number of iterations was 22. We took 22 such iterations for us to finally get the root. Does that really happen over here also? So we define the function. The function is the same as before, but in addition, we also have to define the derivative. Derivative of this is 2x minus 5. So we define the derivative also. So I created this new function called as Newton-Raphson. So it takes the initial guess value. You see the inputs here. Here the bisection method, we have to give the two guess values and the epsilon, the tolerance, which I'm keeping it as default. But here in Newton-Raphson, you don't need two guess values, you just need one guess value. That is going to be my starting value. Then we find out h. H is nothing but this quantity. And just for my convenience, this quantity I'm just calling it as h. H is simply fi divided by f prime I. That means the next point will be simply xi minus hi. Okay, so that is your h. So h is equal to the value of the function divided by the value of the derivative. Okay, so again we have to do some kind of preliminary checks. The preliminary checks is if the value of the derivative is small, if it is almost 0, if it is less than epsilon. Value of the function is value of the derivative. When does the derivative become 0? If the tangent becomes horizontal. If the tangent becomes horizontal, the derivative will become 0. So if the tangent becomes horizontal, then you will not have any intersection. The tangent will intersect at the x-axis at infinity. So that iterations will never proceed. Okay. So we check. This is a preliminary check. We cannot find out the root. So you have to choose a better guess. Okay. Then we print this just like how we had printed the first line here, the columns. We print out the first line here, the columns here. Then I want to keep track of the number of iterations. We do it like this. Then what you do is we have to check. We have to check until this fi by h fi prime. Okay, until this becomes extremely small. Because when this becomes extremely small, okay, when this becomes extremely small, this quantity, when it becomes extremely small, then xi and xi plus 1, they will be very close to each other, right? When fi by fi prime, if this becomes extremely small, then xi plus 1 will be almost equal to xi. That means you are very close to the root. Okay, because as you can see, progressively these points are getting closer and closer. So that is going to be the condition that we are going to use. Okay, so we have this one. We check as long as the h is greater than epsilon, then you print out the value of I, you print out the value of h, and you print out the x0 value, current value of x. You update I, then you go to the next h, next value. Next value is simply x current value minus h. Okay, next value is current value minus h. You do that. Then if suppose again you find out the derivative is 0, if it is almost 0, then you can again, you have to give up, and you have just give this command that I cannot find the root, so try a different guess. Okay, and go out of this. Then you find out the h. Okay, update the value of h, and then whatever you get at the end, you return. Okay, so if the moment it becomes h becomes much smaller than epsilon, immediately if it becomes smaller, then you just return immediately. Okay, so this is how you can proceed. So here I take from the user the first guess. Okay, then the epsilon value, okay, which you can I'm keeping it as constant here. Then if the epsilon value, the value of the value that I have given a, if the value of the function is less than epsilon, that means I am very close to the root. I'm very close to the root. You don't have to do all this, the bisection, you don't have to do that. So the answer, the guess that you have given, that itself is a acceptable estimate of the root. So hence the root is this. If that is not the case, then you proceed and do your iterations. Okay, do your iterations. And then here also again, you see the function is returning false. If suppose you cannot find the root, the function returns false. So if the root, if it is false, then we just say using the bisection method, the root has been estimated. So if it is not false, okay, if it is false, then this will not happen. If it is not false, if it does not return these false values, that means we have successfully used the bisection method, and the root has been estimated to be this, and we display the root and we plot them. Okay, so let's run this. We use the same one here. One guess was 2, another one was 10. So let's take 10 as the guess and see how many iterations does it take. So guess value, I take it as 10. You see, only 4 iterations. That's it. It's much faster. Here it has taken 22 iterations to reach 4.791. Here it has taken only 4 iterations to reach 4.791. Let's find out the other root. Other root, minus 10. Only 5 iterations. Earlier, I think that when we had taken minus 10 here, that also had taken more than 20 iterations. So this proves that the Newton-Raphson method is much faster than the bisection method. Any questions? Any questions? Okay, if there are no questions, then let me proceed to the trapezoidal rule for numerical integration. In this example, we are trying to integrate this function 1 by 1 plus x square. So we are trying to integrate this function from a to b. So we create this. We create this linspace. Okay, this one just I had kept this for testing out some things, so don't worry about this one. Don't worry about this one. I'm going to delete this later. Okay, so this is how we are doing the integration. So first I define the function. The function is f of x, right? So the idea of numerical integration is you're not doing analytical integration. Using the values of the function itself, we are finding out what is this integral. That's the whole idea of numerical integration. Okay, so here I have imported one more package. This is from SciPy. From SciPy, there is in the SciPy package there is a module called as integrate, and I'm just using an alias called as SPI, SciPy integrate. Why I'm doing that is because I want to check the answer that I got, how close it is to the answer that is provided by some built-in function, some function which is provided by Python itself. So there is a function called as traps. It also does this trapezoidal rule. Okay, it does that. So we can verify if that indeed is the case. So what we do is in the trapezoidal rule, I think I have the slides here, just to recap. Trapezoidal rule is here, yes. Okay, so this is the trapezoidal rule, just to recap. So we want to integrate, this is the function, we want to integrate from A to B. Okay, so first what we do is, we basically divide this from A to B, we divide this into n number of intervals. Okay, and the step size is h. So h is given as b minus a by n. Okay, and we rename these points, these intervals, x0, x1, x2, all the way till, because there are 5 divisions, n divisions means you'll go from x0 to xn. Okay, x0 is a and n is b. Now what you do is we approximate each of these. Okay, we approximate using a trapezium. Okay, using a trapezoid, you approximate each of these as trapezoids. Then what you do is you find out what are the areas of these trapezoids. Okay, find out the areas of these trapezoids and you just add them together. Okay, so area of the first trapezoid is this, second trapezoid is this. I'm sure the derivation has been done already, and you add all of them together and then you get a approximation of the value of the integral. Okay, and the value of the integral is given by this formula. The value of the integral is approximately equal to this. This is what we need to keep in mind. The value of the integral is h by 2 into s1 plus s2. What is s1 plus s2? S1 is the sum of the first and the last value of the function. What is s1? S1 is the first and the last one. This f0 and f5, f0 and fn, the sum of these two, that is s1. And everything else, whatever is there, f1, f2, f3, f4, okay, all of them you add them together and multiply by 2. Okay, all of them from 1 to n minus 1, you add them together and multiply by 2, that is your s2. Add s1 and s2 and multiply with h by 2, that is going to give the integral that we are looking for. So this basically does that. Okay, so trapezoidal, it just calculates this given a and b. If you give a and b values for a given value of n, it just calculates this. It just calculates this one. It creates a linear space between them. It calculates h. Then it calculates s1. What is s1? As per this formula, s1 is f0 plus fn. It is f0 plus fn. That is, we start with the starting value. Okay, this is what we do. We will do at the starting value. Then s2 is equal to 0 because we are having just one single trapezoid. We are having just one trapezoid. This is the most basic one. We are just having one trapezoid. So s2 is 0. There are only two functions, first and the last one. s2 is 0. Okay. Then for I, we take the range from 1 to n. Now you proceed, and when you proceed, we find out s2. We just add them up. Okay. We just add them up. We do this summation we do. Okay, from 1 all the way till n, we just add up all of them from 1 all the way till n, because you remember we are using the range. That means n is not included. That means you're going from 1 to n minus 1. You're going from 1 to n minus 1. Then what you do is you just add to s2, you just keep on adding. So that is going to give me this summation, 2 into fxi. So that's going to give us s2. Then lastly, you just have return h by 2. Return h by 2 into s1 plus s2. So I have just used this slide. I have just translated over here. So this is going to calculate the trapezoidal rule. Use the trapezoidal rule to calculate for given a, b, and n. But now I want accurate values, so I should have some kind of a epsilon. You can see here, when will this result be accurate? When will the result be accurate? If we have more number of divisions. Obviously, if you have more number of divisions. So what we can do is, we can start with some n and then we can keep on increasing the values number of n. N is equal to 1. Okay, if you have just one division, then what is that? Next, n is equal to 2. What is the integral? Find out the difference between the values. If the difference between these two values, if it is less than some epsilon, then that means we don't have to subdivide. We don't need any more subdivisions. So that is going to perform the numerical integration. Okay, so we choose I0 as the initial estimate. Initial estimate will be simply, there is only one trapezoid. There's only one trapezoid. That is, this is the trapezoid. So it finds out what is the area of the trapezoid. Then you start with n equal to 2. Okay, then you call the trapezoidal rule a, b, and n. For 2 you do that. Okay, then that will give you the next one. After 2 divisions, it gives us the next one. Then you have this condition. The condition is for no division, for only one division, and for 2 divisions, value of the integral you find out. If it is greater than the tolerance, then you go inside. Then what you do is I0, the whatever is for 2 divisions, for 2 number of intervals, whatever was the integral, that becomes the starting value of the integral. Then the number of divisions will increase. It will become 1. It will increase by 1. Then you call the trapezoidal rule again. Now you are calling this for 3 divisions. then again you check whether the present integral and the previous integral value, if the difference between them is greater than epsilon naught. If it is not, then you increase 3 divisions, 4 divisions, 5 divisions. You keep on calculating the trapezoidal rule again and again and again. Eventually, when between two integrals, if it becomes less than epsilon, then it is going to return this value. Okay, and this is what happens here. A and B, you choose the lower limit of integration and upper limit of integration. I, you do this numerical integration, you execute this, okay, then print the integral, then you create this, okay, same thing, you linspace and you create this function, and using this in this package that we have, the package that we have as this scipy.integrate, over there I call this traps function and I calculate what is the integral, okay. So let's run this. We'll do this from limit of integration. Let's do from 1 to 6. 1 to 6, the integration, that the value that I have got is this one. From our trapezoidal rule that we have got this, and the trapezoidal rule which is implemented by Python, the value is this. It's close, it's both are same. Till 4 decimal places, they are same. The difference starts at the 5th decimal place. From here onwards, there is going to be a difference between the two. Because of course, this traps, it is highly, custom, it's highly optimized. That's the reason. Okay, so that's your trapezoidal rule. Next, we have the Simpson's 1/3 rule. I'll quickly go through this. Simpson's 1/3 rule. In Simpson's 1/3 rule, you have to have even number of divisions. Simpson's 1/3 rule, you have to have even number of divisions. Here, h by 3 divided by h by 3 into s1 plus s2 plus s3. s1 is same, first and the last one, add them up together. Then you add up all the odd indices at odd intervals. You just add them up into 4, that is s2. At even intervals, you add them up into 2, that is going to be s3. So s1, s2, s3 you calculate, add them together, that is going to give you the integral. So this is what is done here. Simpson's 1/3 rule, this is what it does. It calculates s2 and s3 are 0. Okay, s2 and s3 are initially 0. Then what you do is, in this range from 1 to n, you check for this condition. What is the condition? You see, you're looking only for odd ones. Whenever it is odd, whenever it is 1, 3, 5 and so on, whenever it is odd, how do you check if a number is odd or not? If you remember the modulo operator, you can use the modulo with 2 to find if it's odd or not. If I modulo 2 is 1, that means it's an odd number. Then you add that to s2. If it's odd, you add it to s2. Okay, else you add it to s3. So once you've done that, then return this value, that is going to be the estimate. So here also same thing, we do 2 successive integrations and find out if the result is less than some tolerance level. If it is, then you display that, you consider that as to be a good estimate of the integral. Okay, so here also I have just compared it with the trapezoidal. There is function for doing Simpson's 1/3 rule also, but I have not because I did not have the time to actually go through that, but we can do that. Simpson's 1/3 we can do. So actually speaking, I should not be using this. Okay, let's compare that with the trapezoidal only and see what happens here. So we'll take the same limits. The limits are as before. The limits are 1 and 6. Run this. So lower limit of integration is 1 and upper limit is 6. So the value that I got is 0.6202. Okay, till 3 decimal places. But of course, you have to keep this in mind. This is due to trapezoidal rule. Okay, so I have to do the same function for Simpson's 1/3 rule. Okay, so maybe I can just quickly go online and see scipy integrate Simpsons. It will be there somewhere. Simps, I think simps is the function. Simps, okay, why? Okay, let's try this out. It's called simps. The function is simps. Simpsons 1 and 6. Yes, this is the Simpsons rule. Here again, till 3 decimal places we are correct. Now this is more accurate. Simpsons 1/3 rule is more accurate. It is the 4th decimal place. Using trapezoidal rule, the 4th decimal place, the value we had got was 3. Okay, but actually it is 2. This is more correct. Okay, it's correct to 4 decimal places. It is actually correct. So that's your Simpson's 1/3 rule. Then lastly, we have solving ordinary differential equations, the Euler's method. This also was done. So let me just quickly recap this Euler's method. It's somewhere over here. Yes, the Euler's method. So we have a we want to solve an ordinary differential equation. Let's say this is the ordinary differential equation that we want to solve. Initial value is given, that is the value of the function at x1 is given. Then what we do is we find the slope at that point, and that is going to give us the next point, okay, after a h. So h is something that you have to give. Then over here again you have the next point, next pair of x and y. Then again you find out the slope using the function, you find out the slope, again you get the next point and the next point. So this is how you can provide. So this is the function, this is the formula that I have used over here, okay. So what it says is the next value of x is equal to present value of x plus h, and the next value of y is equal to present value of y plus h into the value of the function at the present value of x and y. So this is what I have done over here, okay. So the function that I have considered here, this is a Gaussian function, okay. This is and I want to find out the analytical solution. This is the differential equation, dy by dx plus xy is equal to 0, y of 0 is equal to 1. We can use Euler's method 0.05. So when you solve this, you'll find the analytical solution to be e to the power minus x squared by 2. This is what you will get. So this is your Gaussian function. So I have created a function which does that calculation for me. So here, what is the function here? Because we write it like this, dy by dx is equal to f of xy. So you take dy by dx, you bring everything else to the right hand side, it becomes minus xy. So f of xy is equal to minus xy. So that's why f of xy gives this. So now what we do is we create two empty arrays. Okay, we create two empty arrays. I gave the initial values x0, y0, then h I give, and what is the maximum till where you want to do the calculations. These are the parameters that I give. Okay, so what is the x now? Now is what is the current value? Current value is whatever is the starting value that I give. Then x, y, these are two lists. I append them to the list. Okay, x dot append is the current value of x, y dot append the current value of y. So while the present value is less than x max, because we have to stop when it reaches x max. So while the present value of x is less than x max, perform these iterations. So we just use, you can just see here, it is just using the same thing, this formula here. You can see here, what is the next value of x? The next value of x is present value of x, x now plus h. X next is x now plus h. Then what is the next value of y? Y next is equal to y now plus h into f at which point? At the present value, because xi, yi, that is the present value of x and y. So you got x next and y next, then that means this x next, y next, that is going to become the present values. So that's why I did this multiple assignment here, and then I just append this to this particular list. So I'm basically making a growing list here. Once that is done, I return this list, okay, and I do this, run this, and I'll plot and show you. So this is what I got, okay. This is the function. This is supposed to be Gaussian because it's not looking, because we are starting from 0. If you start from somewhere over here, you will get it will look more like a Gaussian. Okay, so I can do that I can do by changing the initial value. So let's say I want to change initial value is x equal to -1, x equal to -1. So all I have to do is find out what is the value of the Gaussian at x equals -1, and that is going to do the same thing. You see here, this gives the plot that we are looking for. So this is your Euler's method. Now next is the Hume's method. Hume's method is another way. In Hume's method, of course, I'll not go into the details of this. I'll just go directly to the formula. The formula is this. This is the formula. Okay. The formula is you find out the next value of x simply as x now plus h. Then the next value of y you can find out using these two values, these two slopes, s1 and s2. And what is s1? S1 is this, and what is s2? S2 is this. So basically that's what I have done here. I have calculated s1. S1 is equal to the value of the function at the present values, x now, y now. What is s2? S2 is the value of the function at xi plus h. Xi plus h is nothing but x next, the next value of x. Okay. And the other parameter is going to be the present value of y plus s1 into h, s1 which has already been calculated, present value of y plus s1 into h. So that is going to give us s1 and s2. So y next, the next value of y will simply be the present value of y plus h by 2 into s1 plus s2, s1 plus s2. This formula I have used. So once you have got this x next and y next, the present value will become the next value. Okay. So what that means, the next values will become the present value. You create a growing list, okay, and then you plot them. Okay, so again, let me just do it from initial values. Let me just change this. Okay, first let me just keep it as it is, run this, So this is using the Hume's method. Okay, same thing. And then this Runge-Kutta for fourth order method. Okay, RK4 method. So this also little bit more involved, but here instead of three slopes, so two slopes, we have four slopes. S1, S2, S3, S4. All of them you have to calculate and put them here. That is going to give us the next value of y. So this is what I have done. S1 is equal to the value of the function at the present values of x and y. S2, the value of the function at present value plus h by 2. And y is the present value plus s1 into h by 2. Okay, so did this here. S3 is equal to x1 present value of x plus h by 2 and present value of y plus s2 into h by 2, and finally s4 is equal to x next plus y now plus s3 into h. So we got s1, s2, s3, s4. Put them over here in this formula, h by 6 into s1 plus 2s2 plus 2s3 plus s4, and when you do that, you create this growing list. Run this again. Oops. Again, you get the function that we are looking for. Okay, you could try this from -1 using -1. That is the initial value. Also, you can try it out. Okay, so this is what it is. So I think with this, I'm done for this workshop. It's exactly 1 o'clock. I think this session was supposed to end at 1 o'clock. It's 1:01. I have taken 1 minute extra to complete the topics. So if you have any questions, you may ask me now.
Sir, here we haven't write the formula or the function in this one, no? LaTeX, using LaTeX. So
Where?
why, sir, we haven't
Where?
used?
Here. You mean here? You mean in this plot?
Yes, sir.
I didn't understand
Here you haven't used LaTeX.
Okay, the reason is because actually the reason is I did not get time to do that. Actually, I can do that. I can just add this here, plt.x label, x. I can do that. It's just that I did not get the time. Okay, my mistake. This should be a string. Okay, I can do that actually. I just did not get the time. It's lack of my excuses, lack of time. I did not get time to do all this part. But you get the idea, right? The idea is the implementation part. You can go ahead and you can, whatever we had done in the previous presentation, no, on Matplotlib, you can do that. You can go ahead and you can make this plot look much more beautiful. Okay, you can do that. Okay, does that answer your question?
Yes, sir. And can you explain once more about that IMSHO? Does that only means opacity?
The IMSHO, you mean scatter? I think I use opacity. That alpha value I have used in scatter plot. I think I have used.
Yes, sir.
Okay. I think the scatter plot is somewhere at the bottom. Here, this one. Is this what you're looking for?
Yes, sir. Yes, sir.
The opacity. So suppose I give this as 1, okay, 1.0. That's a default value. It is just going to remain smudged like you don't get to see any of these, the density variations. Where are the stars more? This entire thing looks like as if it's having uniform density. Either there is a star or there is no star, but that's not the case. You can see that if you, make it more, transparent. That you can do by using the alpha value. If I make it as, only 10%, alpha is the opacity, okay? If I make it only 10% opacity, then you see it becomes a little bit more. You see here, wherever there are single points, if you open the figure, you can see here the single points. Wherever we have single points, they become very faint. But wherever there is an overlap, you can see wherever there is an overlap, that overlap region, it becomes darker. So just by looking at it, you can see here, these are the places where it's very dark. You can actually go around, you can reduce this even more. You can reduce the opacity even more. I could make it like 5% also you can make. 5% fraction, 5% means 0.05, 0.05 is going to make it even faint. You'll be able to see the density variations even more. Okay. So the alpha is opacity. Alpha is opacity. Lower the value of alpha, less will be less opaque these circles are going to be. Okay.
Okay, sir. And IMSHO?
And which one? IMSHO. Yes.
IMSHO.
Okay. IMSHO is this one. IMSHO is basically it creates an image. IMSHO means image. So I have a grid. I have a grid like this. Let's say I have a grid like this. At this point there is a 0. At this point there is a, let's say, 255. 0 will be interpreted as a black. 255 will be interpreted as white. Some other place, let's say we have 136. That will be a shade of gray. So all the way from 0 to 250, wherever there is variations, that becomes this image. So you can convert your image into a matrix, because after all, that's what an image is. It's basically a matrix of grayscale values. Okay, so IMSHO basically does that. So I created a grid, and in this grid, basically, where am I getting this grid data from? I'm getting this grid data from this file called as circular. Okay, from this file called as circular, I'm getting X values, Y values, and some more values. That other value is the last column. The third column, it has something like intensity values. Okay, so what I did was I created using the first and second. IMSHO, what it does is using the first and the second column, it creates the mesh grid, and then it puts the intensity values, it puts it on top of that each and every combination of X and Y. For every combination X and Y, it gives one value, and I have converted it into grayscale. So IMSHO basically converts a matrix into an image. Okay, so IMSHO is basically, let me add this here. So we can say that, oops, IMSHO, the IMSHO function creates an image using a two-dimensional matrix. Okay, so this is what an IMSHO basically does. You're creating an image. Okay, so instead of circular data, if you give me a black and white image, okay, and of all at each and every place, if the corresponding grayscale values are given, you'll be able to see your own image. In fact, if you go to that matplotlib, that examples page, no, you will find the plotting of images. There are lots of examples. You can actually plot images also using matplotlib. Okay. Any other question? Does that answer your question, Bonmari?
Yes, sir.
Okay. Any other questions? If you have any other further more detail, like in in greater detail, then you can always feel free to get in touch with me. Okay, I'll be more than happy to help you out. Samrat, are you there?
Yes.
Yeah. So what do we do now?
Since there are not many questions, maybe we can just have a short valedictory and we can
Okay.
finish.
Okay. Sure.
So let us take some feedback from the participants, no?
Yeah.
So participants, please give your suggestions or criticisms, whatever. If you have anything in your mind, you can share it with us. Suggestion for improvement will be really appreciated. So we would like to know, especially from the participants who are not from Don Bosco, please feel free to give your suggestion. Even our own students also, if you have any suggestion, you can please tell us.
Yeah. Even the new students also. You can list. Old students, they have been seeing our faces. New students, would like to hear from them.
Yes. Maybe someone from MSc first semester? Is there anyone from MSc first semester?
Yeah, we have a lot of students here from MSc first semester. I can
Yes.
see Angeline is there, Adelphi is there, Calvin Star,
So please tell us how
Dishani.
have you liked the workshop? Was it helpful to you, or it required some more classes or some new topics, or whether the topics were too many for you? Please tell us.
Hello, sir. My name is Larry Gopal Nobat. This workshop has been very, very helpful, but the only problem is that I don't have much of a computer background. So I learned something. I got introduced into new things, so I got excited. And the only problem is that most of the things that Sir Parag taught was almost everything was a bouncer for me.
Okay. So, see, we will be sharing all the videos with you. Okay. So, you can go through the videos again, and we will also share with you the study materials, even the ones given by our invited speaker. So, I believe if you have any difficulty at that time, we are also there. You can always approach us individually, and we'll be happy to help you out. And that holds for all the participants here. You can see the videos, and if there are doubts, you can always discuss these things with us, and we'll be happy to help you out. It's actually not possible to learn everything within 2 to 3 days. It is almost humanly impossible, but our basic idea is to give you some concept about this programming language and computational physics. And even if you have got say 20% or 30% of that, I would say that is good enough. Rest of the things you can learn, through the lecture videos which will be shared, and you can also discuss with your friends. You can learn from each other also. What do you say, Parag?
What I believe is, even if suppose like not even 20% also, even if you got 0% out of this, but at least if you're inspired and curious to learn more about this, that itself is a big step ahead actually in this direction. Because these workshops, it's not meant to be a full course, like I said, no, in day for yesterday, it's not meant to be a full course. It is just meant to be an appetizer, just to give you a taste of what are the things that you can do, what all are available for you, what are the tools that are available to you. So if you are inspired and then you feel that no, this is something that I need to really learn, then yes, the help is already there, always there for you. So that's the whole purpose of this workshop. And if you are interested and then you find that this to be very interesting and you're inspired by this, then I think in that aspect the workshop is quite successful, because that's the whole purpose of the workshop. So that's what I believe. So I think we have a participant out from outside. I'm able to recognize his name is Pranjal Pratim Gogoi. I think he's here. Pranjal, it'll be nice if we can get some feedback from you.
Jivan is not there, no, today?
Jivan, I did not see.
Okay. Till yesterday, he was attending all the sessions.
Pranjal Pratim Gogoi, can you hear me?
Yes,
Yeah,
he can.
he's texting. So it'll be nice if we can get some feedback from you, Pranjal. You can text also. Okay, while he's giving his feedback, maybe some of our other students from MSc, if they can also share some more things. Maybe some BSc students, BSc first semester students. I see many of them here.
Hello, good afternoon, sir.
Yeah, Mehul from MSc first semester.
Yes, sir. Sir,
Yeah.
sir, I followed, but sir, the problem was the like in the meantime, like after 1 hour or like 1.5 hours, like it was consuming data at a very high speed, so I
Okay.
couldn't follow the full video lecture. I was listening to the audio, like very like later half of the.
So for that, your YouTube video will be available. Already the day one videos are already uploaded. Day two and today's lectures will be available within a day or two. So don't worry about that. You can just watch it whenever you can. Okay.
I tried to follow the audio as much as I can in the later halves. Yeah, so
I'll also provide you all the study material, all the lectures, everything. I'll be providing to you. So that way, it'll be like almost as if you're learning it on your own at your own pace. So don't worry about that. We'll make sure that all the resources are available to you. Okay.
thank you, sir.
Any other students from BSc?
I think some comments are coming in the chat box also.
Yes. Dishani has written.
Yes.
Okay, she finds Python very interesting and she wants to know more about Python. So what should I do to know more about Python? Well, I mean, I learned Python. Nobody taught me Python. I learned it on my own. Okay, so like I said, lots of resources are available online. So it's just a matter of just going out there and finding the resources. But in your case, you're going to be much lucky because we all are here in the department. So if you want to learn more, you can always feel free to come and get in touch with me. I'll be more than happy to show you.
Dishani is from MSc.
Yes, MSc first semester.
MSc first semester. Okay, Dishani, maybe I can take a suggestion from your observation. Right now, the computational physics course that we have in third semester MSc is implemented by either C or Fortran language. So maybe in our board of studies meeting, we can also think of the option of putting Python as another option. So maybe we
Yes,
can think. By the time you will be in your
very progressive step.
yes, by the time you will be in your third semester, you will also have the option of using Python for computational physics over and above Fortran or C. So that can be done. Of course, if the board of studies accepts it, we will try to put it. Next thing is that for BSc students, it is already there. They are being taught computational physics using Python language also, Python language only rather. So if you have no class during that time, sometimes you can also sit in their classes, in their lab classes, and you can learn from there also. So that is another option.
Okay, this is a very specific. Chris has asked a very specific question: how to add matplotlib to Python? Okay, I can show you that. There's just a set of steps that you have to do. I can show you that. Don't worry about it. What about some of our existing students, like old students? Maybe it'll be nice to hear them again.
Our past students are also there. Samarjit is there.
Samarjit, yes, Samarjit.
Samarjit,
would you like to speak?
in the meantime, I think Parag, you can show him. You can show Cheris how to add.
Chris.
Chris.
I'll show him. We'll get in touch with him and I'll show him.
Okay. Okay.
I think everybody has reached some kind of a saturation by now.
Yeah,
So,
also correct. Yeah, you can.
including me also.
Okay. So I think there are not many more feedbacks. So let me thank our main resource person, Mr. Parag Bhattacharya. I really appreciate you, Parag. I don't know how you managed to take so many classes at a stretch. And also covering so many topics. Earlier, I thought that I am in the university who can complete syllabus well in time, but now I have to consider it. You can complete any syllabus in any amount of time. in any small amount of time. So really, I thank you. I appreciate you for your time.
Thank you. Thank
And
you.
let me also put my thanks for the invited speaker in our Q.
I would like to appreciate our invited speaker because he has been attending all the technical sessions also. Because I see him being present in the now he has left, but he has been with us, like not just for the inaugural keynote address, but all the way through every session. I have been actually seeing him.
Oh, that is really nice. Okay. Anything from your side, Parag?
Yeah, I think I'm done. I think I've spoken enough.
Okay. So should we call it a day?
I think Pranjal has
Oh,
given
Pranjal
some.
has.
Okay, I'll just read out. I'm very happy to participate in the workshop. Thank you very much, SG, PB, and SD sir. I didn't have any knowledge on Python before. Attending this workshop, I get to know more, but I have to exercise a lot to learn more on Python. Yes, of course. I mean, it takes practice. So, Pranjal, what I suggest is you can just take up something like a project for yourself. Suppose you have learned some concept in physics, just try to implement that, just see if you can implement that in Python. So when you do that, when you get a project for yourself, that will be something which will be outside a textbook, and that will force you to, that will stimulate you to actually think also in that direction. So in that way you will actually learn much more. Personally, I have learned Python because when I tried to solve a problem, let's say from my research, that's when I found that I have learned Python some more about Python. And there are lots of online forums which are available where people are more than happy to actually help you. Whenever you have a problem, you can just post, and discussion boards, people will be more than happy to actually help you out. So that way will actually, it takes time, it takes a lot of time, and it takes a lot of patience also. Bonmoiri, she has written, although it's quite difficult to understand a coding language in the 3 days, but thanks to our respective teachers for delivering the entire workshop in a much easier and understandable way as you can. Thank you for the efforts. Thank you so much for your kind words, Bonmoiri.
Excuse me, sir.
Yeah,
Sir, I had one question.
yeah,
Sir,
tell
when
me.
giving the sunspot data,
Huh.
yes, sir. Like sun is not observed from all sides at all the time. That's what I was thinking.
Yeah, I
Shouldn't
mean
be
that's
the
the fluctuation happens because of the rotation of the sun also. This data that is shown here, that is the data for that was observed from the Earth from 1749 till
sir,
like
but sir,
2000.
at any instant of time, we cannot observe the like if there is
Yeah,
some
but
spot on the other side of the sun, and by the time the sun
yeah,
rotates,
of course.
it
I mean,
dissipates.
of course. But this is what is observed. This is observational data. This is not the absolute truth. This is what has been observed from the Earth every month since 1749. This is not the absolute truth. It's like that. That story is there. There is an elephant, and then four blind people were asked to describe the elephant. So one person, he caught the trunk and he said that the elephant looks like a snake. Another one, felt the legs and he said that the elephant is like a tree. Another person, he caught the tail and he said the elephant is like a snake, right? So it's just perspective. The truth is that it's the elephant is from the different person's perspective. So the data which is given is the perspective from the earth, right? From 1749 to this one. That does not give a measure of the actual number of sunspots all over the sun at that point. So that way is
Yes,
correct. So this is just the
sir.
observational data.
Sir, one thing I have question
Yeah.
there. Is there any technique available to observe the sun 24/7 from all angles?
Okay, let's just talk about this. I don't think that will be that's beyond the context of this workshop, but we can talk about this. Okay, we can talk about. There are lots of missions. We can talk about this.
Okay, sir. Yeah, thank you, sir.
Yeah. Okay, Pranjal, he has thanked us, and then Apsana, she has also thanked us. Thank you. Okay, Gyati Gyut. Okay, 10 Q user, 10 questions. I'm not able to understand this. 10 Q. Do you have any questions, Gyati? I'm not able to understand this. 10QU. What is that? Okay, thank you. Thank you, sir. Okay, okay.
Okay.
I think it means thank you. Okay. This only shows how old we have become. Like this, I think this is the kind of lingo that kids use. So I'm not able to understand. It only is a proof that I'm getting old. Anybody else would like to add something? Raktim is there, Raktim from BSc. I see him attending all the lectures. Raktim, can you give a few words? Share your thoughts. Okay, Queenisha, she thanks all the teachers. Thank you, Queenisha. Samrat, I think we can proceed, right?
Yes, we can proceed. And
Chris, wait, one more comment. Chris. Okay, first of all, Chris, is Chris same as Dondor? Chris and Dondor, are they the same person? I think. Okay, yeah, that's Dondor. I know you as Dondor. I mean, like, I suddenly reading as Chris, I'm finding it a little different. Okay, thank you. He says thank you for the wonderful insights on Python. It was very informative and inspired me to learn more. Okay, if it has inspired you, that means this workshop is a success.
yeah. So, Parag, should we?
Yeah, I think we can.
We can
go ahead
conclude.
now.
We can conclude. Your certificates will be given within a few days.
1 week. Yeah,
One
within
week.
1 week, you'll get the certificates.
So, thank you. Thank you for attending all the sessions, or most of the sessions. So, yeah. So let us conclude. Thank you all.